Good morning, everyone. So I'll just let everyone grab a seat and settle in. So yeah, good morning. Strange how Friday always seems a little bit quieter than Thursday morning. Don't know why. We've got a good day of content today. We're going to kick us off with Beck from Cisco, and he's going to be talking about open source traffic generation.
Good morning. Hope you all had a good night last night. Had some fun. I'm going to talk about a open source traffic generator called T-Rex, which is from Cisco. I was having a chat with a friend of mine yesterday. It was like, oh, what's Cisco got to do with open source? I guess we just couldn't find a product manager for it. Right, so I started with a bit of like a sketch in my head. Then I thought I'll be a bit cheeky to ask ChatGPT, since it was quite popular. This is what I got, which was not very helpful, because it's too much for a slide. And I did try to ask ChatGPT whether they can give me a full presentation, and that wasn't good. So this is the only slide which is not from a human. So what is T-Rex? If you go to T-Rex website, it'll tell you it's a realistic traffic generator. So I mean, realistic mean different things to different people, I'm sure. Why they called it realistic traffic generator, it was because it sort of came about when a couple of dev engineers were working on a customer problem. So a customer reported an issue with a feature called nbar, which is like stuff like a similar DPI feature. So the feature itself is actually quite complicated. The engineers actually did some internal testing, but it was only with like a few gig worth of traffic. So they couldn't really recreate the customer issue. And they looked at what they had as options at the time. So commercial traffic generation appliance, they're really expensive. And if you want to do fancy stuff, at least at the time, it wasn't that flexible. So they basically went ahead, say, let's create something, because it turned out with the DPDK, you can actually do quite a bit of traffic generation with just x86 and a server NIC. So they started with a UCS server. I mean, you can actually use any x86 server and Intel NICs. We now support more NICs, not just Intel. And the idea was that if we could capture traffic, or we could capture different types of traffic as PCAPs, and we can replay those PCAPs, and you can control like how frequent you can replay those PCAPs. And the installation is supposed to be quite simple. It's pretty much like no installation. You just get the tar file, unzip it, and that's fine. Everything, all the library is actually included in the directory. So this is actually a very general idea. So this is actually common setup and topology when you do some testing. So you have a Doot device on the testing. Then you have a host that runs T-Rex. Now the idea at the time was really focusing on stateful traffic generation because that was the actual issue. We'll talk about the configuration a bit later. So T-Rex should be able to generate based on PCAPs, client and server flows. That's the basic idea. What we have today is we actually have a lot more supported NICs. If you read the documentation, it will say the officially supported OS would be Red Hat. But I've actually tried Ubuntu, and it actually works fine. Although there is a line saying if you use Mellanox connected X4, RHEL is the only OS that works. It also works with VMs. With VMs, we support common vNICs. The only downside is that performance is not as good as physical NICs. And if you do SR RV, virtual functions are also supported. You can get a lot more detail on the documentation. There's also a lot more modes that are supported because the engineers started with stateful. Then they realized stateful is actually sort of like a niche when it comes to testing in networking. Because a lot of the time, if we say you did a network design, you want to validate your design, most of the testing will probably be stateless because you want to understand the convergence, you want to understand whether traffic is being matched or properly processed by quads. There's also protocol emulation. So T-Rex itself can actually act as a protocol client or sometimes protocol servers. And also bird integration for prefix generation. So what I'm going to talk about is stateful and stateless. Right. To actually use T-Rex is actually pretty straightforward, but you sort of need a host that has at a minimum of 3 interfaces. Because once T-Rex takes control, your traffic generation port won't be available to a kernel anymore, which means if you remote in, you only have 2 NICs, you'll lose your access. So you have a management interface and 2 or more traffic generation interface. There are actually 2 major configuration files. One is your port configuration file. This one should pretty much be static. So once things are set up, you don't need to worry too much about it unless you change your NICs. The other one is traffic generation config file. This varies from different types of tests that you want to do. Very important thing is to note down the PCIe address of your test generation interface. The device under test also needs to have necessary routing because T-Rex works in the model in that you have IP here, so you have a 1/30 or /24 segment here. The actual traffic generated will be behind this IP segment. So you need to configure additional routing on the device under test. Right, this is an example port configuration. Most important thing here is to specify which ports that you're actually using for traffic generation. There's also a platform section configuring your thread allocation, right? So I was using a 6-core i5 processor. So basically, you can keep 1 thread for your master thread and another one for your latency. So this latency thread basically deals with any RX processing, which is very light because most of the RX processing is offloaded. And the rest of the thread, you can use them as traffic generation thread. There is, like if you're running this on VM or your laptop, there is a low-end mode, which you don't have to plan your thread allocation, but performance will be lower. IP address and the gateway are the most important configuration. MAC address configuration are actually optional. I have them here so that the T-Rex host doesn't need to do ARP. Right, this is a very simple stateful flow configuration. This is, if you read the documentation, they will say, oh, this is the sort of like hello world equivalent to T-Rex. We have, if you notice this file is actually included when you download T-Rex. There's actually lots of example configurations which you can just use directly and do a bit of, do a slight tweak to suit for your test setup. We have the client configuration and server address block configuration. And we have a configuration for the PCAP and a rate, which is connection per second. I'll explain the CPS later. But this PCAP is basically any PCAP you want to use for traffic. And you can actually have many different PCAPs for different types of protocols that you want to test. This is just an example. I was just trying to read the content of this PCAP. What T-Rex does is it will take the content of the PCAP and change the source destination, so basically your headers, based on the configuration here. So it doesn't matter where it says it's 22 something to 21. I'll show you a actual PCAP with the generated traffic. Connection per second. This is if you want to understand and calculate for PPS, for stateful. Everything in T-Rex is flow-based. So each single row is actually a flow. How many packets you have in a flow depends on the PCAP. So if you have 2 packets in your PCAP, then you have 2 packets per flow. And you can choose to do flow multiple times per second. And we can amplify that again, so we can easily get millions of PPS. Right, this is a, hang on. This is a bit hard to read, but this is basically, I've started the DNS traffic. So this is really simple. This is DNS request and then a reply. So there's only 2 packets. You see, we actually, because traffic is actually bidirectional, so it's actually 2 packets per second and 1 connection per second. Because the one connection per second was in the configuration. And you also see whether you have any drops here. So this page is actually updated every half a second. Now this is actually packet capture of the generated traffic. You would notice we have the header, source and destination IP address is changed. This is different from the actual PCAP. This is basically just a packet plot. So we have time on the axis, and y-axis is the flow. You can amplify the traffic. Here what I'm doing is when I start the traffic generation with a CLI, you can put a multiplier here. What I've put here is 1 million. T-Rex will calculate whether your layer 1 rate is over your NIC port. So if you configure too high a number, because I tried with 10 million using the Intel X520, it will basically just give me an error saying no, it's over the L1 rate. Right. You can do multiple different types of traffic. So you can have a huge list of different PCAPs. to come up with a really fancy or complicated flow. This is just a example of a HTTP plus DNS. So the blue ones are the DNS. We've configured the DNS to be 10 connections per second. So this x-axis here is actually over a second. And we actually have 10 of the flows. The HTTP, you will see we have 2 connections per second. So that's the 2 HTTP flows. Right. There's a lot more included examples that you can play with and tweak as you need. Right. Stateless. Stateless is probably, like if you're a network engineer, probably more familiar with stateless traffic generation. Stateless actually scales a lot better than stateful, which is obvious. And you can easily do millions of PPS with stateless. We use a tool called Scapy to craft a packet. The difference here is the initial, the very early stateful configuration, we use the YAML as the configuration file. Whereas for stateless, configuration file is Python. You don't actually need to be a programmer to do it. You just need to be able to read and understand what's there to actually change the configuration file. And you can do various modes. You can do continuous, you can do burst, you can do multi-burst. And the rates, you can specify them as PPS, BPS, or just percentage of the port. This is just a demonstration of what the streams of stateless traffic generation can be. So stream 1 is actually a continuous stream. I can configure multiple streams and generate them at the same time in a single profile. So you can have a burst stream. You can also have a stream that depends on another stream. So you can actually do some quite fancy stuff with it. The actual interaction with T-Rex also changed with stateless. So previously, the example was you just type a CLI with options, right? Just like a normal Linux command. You give it an argument, it will run as your configuration and your argument. But with stateless, we need to start a T-Rex server first, and then in a separate terminal, or if you prefer to put it into the background process, we can either go to a T-Rex console, or you can access it through API. It does have a GUI. I'd rather not to go to the GUI because like the latest release of T-Rex actually broke the GUI. So if you use the latest T-Rex, the GUI wouldn't work. You need to go back to probably 2.87 to be able to use GUI. But CLI, T-Rex console has pretty much all the features and functionalities of the GUI. Right, this may look a bit intimidating, right? So you don't need to worry about a lot of them. We just have a configuration on a source and a destination for the packets to be generated, and it's UDP. That's a D port. That's your source port. That's the padding. So yeah, you can play with those fields. And once you have this, all we do is we start T-Rex server with T-Rex-I. It'll tell you I'm seeing 2 interfaces, and these 2 interfaces would be the traffic generation port. And then go into T-Rex console. When you go into T-Rex console, you can then try to generate the traffic. So this is generating stateless. Well, I have -f for the configuration file, which is the file in the previous slide, and your rate. So I'm trying to do 5 Gbps. Now, this is not layer 1 rate. This is actually layer 2 rate. So if you want to specify layer 1 rate, you can do 5 Gbps, then L1. You can find the actual syntax in the documentation. Right. And this is, once you've started your traffic, you can go into the TUI or TUI. This is basically the traffic status of the stateless traffic generation. Now you'll notice here, I'm seeing some drop rate, and this is port 0, this is port 1. Port 1 looks fine. Port 0 has no RX, right? Now the reason is we're generating from both ports, but the source and destination is the same. So your routing is not working. Right? This is something you don't typically do. So what you do is you go to a different example. Right? You don't need to write your own. You just go to a different example where they do define a bidirectional flow and just use that. And once you have a bidirectional flow, make sure that matches your routing configuration. You'll see your traffic generation should be all good. Right. We don't have drop rates here. We have RX as well. Right. That is my talk. There's some references on T-Rex. We have 2 YouTube videos. One was the Cisco live session from the creator of T-Rex, and then non-Cisco T-Rex live demo.
Any questions for Beck at all? One thing I did notice when browsing your website just before, or the T-Rex website, is it does seem to have an invalid cert, so you might want to let someone know at Cisco. Due to a bad certificate authority, at least from my browser's point of view.
Yeah, I think given the GUI is not working, that was not too surprising.
I think no more questions. So next up, we've got another attendee from the West Island. We've got Mark Smith here to talk about MTUs, MRUs and PMTUs. Thank you, Mark.
How do I try this? Okay, yes. Okay, excellent, thank you. I need these guys to want it. I could do it backwards. I maybe didn't drink enough last night too to do it backwards. All right, my name's Mark Smith. I'm from the West Island. We're angry over there because it's so big. Today I'm going to talk about MTUs, MAUs and PMTUs. Right. Okay, so none of what I'm going to talk about is really new. Most of people here will know some of it, some might even know all of it. My main goal is to put in one presentation. One of the things I've noticed over the recent years is people are not fully understanding MTUs and MAUs and PMTUs. Used to be a lot easier in the 90s because things you couldn't change, but I thought I'd talk about that because I've seen some recent outages because of MTU misunderstandings, so that's some of my motivation. There's really 2 fundamental questions that I want to try and answer today. When shouldn't you change MTUs and when should you? Pretty straightforward. This is my little Mr. Pizza takeaway symbol, so if you see that on a slide, that's one of the key takeaways. So firstly on to MTUs and MAUs. What does MTU stand for? I must admit I've got in the habit of calling it maximum transmit unit rather than maximum transmission unit. There's an RFC with an error in the title, it calls it maximum transit unit. But they're maximum transmission units. In this presentation, we're pretty much talking about Ethernet MTUs. The default MTU for Ethernet is 1500 octets, and an octet is an 8-bit byte, because back in the 50s and 60s and 70s, there were 5-bit bytes and 6-bit bytes, so octet is the correct term you'll see. So this presentation is about Ethernet. Obviously, we've had a lot of other layer 2s over the years. PVP's still around a bit, but all the rest have died. However, you know, these concepts that we're going to talk about will still apply to other layer 2s if any come along. So here's a question. On this diagram, we've got a host on the left. Admittedly, it's not really possibly as old as that, but I like that symbol for my computer, so I use it. There's a MTU of 1500 on the left and an MTU of 1514 on the right. The question is this an MTU mismatch? The trouble we have today is, what does MTU describe? It's actually quite a vague term, maximum transmission unit. Is it talking about what can be carried in a frame or packet? Is it the size of the frame or packet, including the payload? Or is it even the bytes or octets that are travelling on the wire? Such a generic term, you can't tell, and that's where some of the confusions come from. I went looking for the IETF's definition. This may not be the authoritative definition, but it was certainly the earliest. IENs, or Internet Engineering Notes, were early versions of RFCs. There was a bit of a crossover, but if you really want to go back in the history of the internet, go and look up Internet Engineering Notes. And this is one, IEN 111. It's the Internet Protocol specification from August 1979. It was the first place I saw MTU defined. And it's the maximum size message that can be transmitted through the next network, and it's called the MTU. The network they're talking about is what we call subnets today, because in 1979 subnets didn't exist. And from memory, classes of addresses didn't exist either. So we just had 256 networks and that was it. I also looked up the Ethernet spec, IEEE's 802.3. You used to be able to download them free for a while, but you can't anymore. But there is no such thing as MTU defined in there, no maximum transmission unit. They call it something else. But there's some ambiguity already and lack of definition. Because of this confusion, I thought about how can we sort of clarify what MTU really stands for, and I've come up with some definitions. I'm going to use these for these presentations. I'm also going to work on an internet draft to define them, because I think it's becoming more and more important to truly understand this. The definitions I've come up with are payload MTU, describing what can be carried, the maximum number of octets that can be carried in a packet or frame. The frame MTU or packet MTU includes the headers of that packet or frame. The full frame MTU or full packet MTU, that's to account for any trailers such as Ethernet's CRC. There's even a version of IP that use trailers on Ethernet. It's a bit obscure. And finally, we have the wire or medium MTU. Sometimes people have been calling things like L1 or L2 MTU, which is probably a bit more useful than just the generic term MTU, but it still doesn't really describe what actually, octets we're referring to. One of the things to realise is that the payload MTU of a frame or packet at a lower layer becomes the packet or frame MTU at the next layer up. So we have an Ethernet frame at the bottom with the Ethernet header and the Ethernet payload. The Ethernet frame MTU, as we just saw a moment ago, the Ethernet header is 14 bytes, and we have the Ethernet payload. If we put an IPv6 or IPv4 or IPX or whatever packet inside that, we have our Ethernet payload MTU being 1500. Well, that becomes the IPv6 packet MTU because, of course, it's including the IPv6 header. If we then look at the IPv6 packet, well, it has a payload MTU as well. That's the maximum payload that we can fit inside the IPv6 header, and in this case, it's 1460 for the standard sort of Ethernet constrained IPv6 packet. So back to our question. Was it an MTU mismatch? Well, our host on the left happened to be running Linux, and we can see that it's showing an MTU of 1500. Well, that's actually on Linux, traditional Cisco iOS, Windows, Mac OS probably, many other operating systems. It's showing you the payload MTU, so it's not counting the Ethernet header there. This MTU is the one that's available to the next level up, to IPv6, to IPv4, etc. On the right, however, that happened to be a Cisco IOSXR router. I didn't have a chance to look at Juniper and other platforms. One of the things that Cisco did when they moved from iOS to IOSXR was they actually change the MTU from being the payload MTU to the layer 2 or the frame MTU. So on the right here we have an MTU of 1514. That's the frame MTU, which means it includes the Ethernet header. If we do our analysis or calculations, our host payload MTU is 1500. Our router frame MTU is 1514, but if we take the Ethernet header off, we get an Ethernet payload MTU of 1500. And since we get matching payload MTUs on the host and on the router, this is not a mismatch, even though initially it looked to be. And in fact, configuration-wise, it probably would look to be a mismatch. So the fundamental goal, when we're possibly changing MTUs, is to match up the payload MTUs on both ends of the link, regardless of the overheads, or not so much ignoring them, but make sure you understand what parameter you're changing, and the goal is to make sure the payload MTUs match up. As an example of a mismatch, and this one I've seen a few times, we have a payload MTU of 1500 on the left, like we just talked about. People have taken that, and it's quite understandable why. They say, oh, well, it's 1500 on the left, so we'll put 1500 on our router. Trouble is, the router's doing a frame MTU, not a payload MTU, so they've actually got a payload MTU of 1486, which is minus the 14. This is definitely a mismatch, and you'll have problems. And this is really raising the issue of you need to know, if you're going to change MTUs, what parameter you're changing. Is it payload, is it layer 2, or is it the frame MTU? How are MTUs used? It's probably straightforward, most people understand this. For hosts, it's really just about when it originates a packet, because they always originate packets, they're the source of all packets, how big can that packet or frame be? We have the frame MTU of 1514, which is a standard frame MTU for Ethernet, means a payload MTU of 1500, and therefore a packet MTU of 1500. Routers use MTUs for two things. Number one, originating, similar to hosts, such as OSPF, V3, or LDP. How big can that be when it's sending it to some other device on the network, including its neighbours? Alternatively, when a router is forwarding a packet, can the forwarded packet fit on the next link in the path? One confusing thing these days is where we have parent and sub-interface MTUs. And this can get confusing, and this, I think, can be some reason why people change MTUs. On the left, I hope you can see it well enough, I've just configured a standard Ethernet lag, a bundle ether under Cisco IOSXR. The default MTU of that is 1514. You can guess by that number that it's a frame MTU, and we should know what it is from our platform. We can also see the underlying member interfaces, the two 10 gig E interfaces, 46 and 47. They too have a frame MTU of 1514. Gets a bit interesting when we do VLAN sub-interfaces with VLAN tags. So, and that's what I've shown on the right. So I've configured a VLAN sub-interface, bundle ether 10.20. Haven't changed the MTUs of anything. It's showing a frame MTU of 1518. It's automatically accounted for the extra 4 octets of the VLAN tag. If we look at our bundle ether true parent lag interface, its MTU is still 1514. And that's because that interface will deal with the untagged, if there are any untagged frames, that interface deals with the untagged frames. You could run IP over that and it will be untagged Ethernet. The underlying two member interfaces though, they have automatically had their MTUs physically increased as well to allow them to accept and receive and process the VLAN tags. This has been all automatic. I haven't changed any MTUs anywhere. This is an important point because I think people sometimes think they might need to adjust things when they are in this sort of scenario. Onto MRU and what it is. It's not very commonly used a term. You do see it occasionally, which is why I'm going to cover it here. So MRU stands for maximum receive unit. The MAU is the maximum receive unit of an interface, and most of the time, the MAU of an interface is usually and implicitly the MTU. It's the equivalent of the MTU, or the same value as the MTU. So if you change your MTU, you're implicitly changing your MAU. You don't see it that much, but here's an example where on an iOS device, if you look up the show controller interface, it actually is showing an MAU parameter there. It's matching the MTU. That sort of implies you can have them different, but I'm pretty sure you can't. But there's just an example of if you ever see MAU referred to in that sort of context, that's what it's referring to. For completeness, we'll have these same definitions: payload MAU, frame MAU, etc. The thing about an MTU mismatch is it's really an MTU and MRU mismatch. So we can see a frame MTU of 1514 on the left host there. This is including the Ethernet header. On our router on the right, this is going back to my misconfiguration example earlier. On the router on the right, we have a frame MTU of 1500. This means the host can send a frame of up to 1514 bytes or octets. The router on the right can't receive 1514 bytes because it's limited to 1500. In the other direction though, things work because the router on the right, the maximum transmission frame it can send is 1500. Well, that will fit in the MRU of the host on the left. And this is where you get some confusion because MTU and MRU mismatches, you get packet loss in one direction but not the other, and it's only some frames, not all of them. And there's the issue. The link can appear to be working, and people commonly think it's working, and depending on various scenarios, you will rarely see any packet loss, but every now and then you can, and then you get woken up in the morning like I was a few weeks ago because of an MTU MAU issue, because BGP went down. Signs of mismatches. Occasional unexplained packet loss. Unnoticed packet loss. Well, I suppose that's not really a sign because you don't notice it. It's really sensitive. Or frame of packet drop counters, and that last one's an important one. Here's an example of how it can happen. We have and this applies to IPv4 too, we have a full-sized IPv6, traditional default full-sized IPv6 packet that's come from the internet on the left. It's been forwarded through the network to the router on the it's come from the right, far left, and it arrives at the router on the far left. For some reason or other, the packet generates a ICMP error message, such as a destination unreachable. Maybe there's no matching route, something like that. One of the things about ICMP, v6 and v4, is that they copy as much of the packet, the trigger packet, into the payload of the ICMP message that will fit within the MTU. So, we start with our IPv6 packet that trigger the message. It's 1500 octets. We add another IPv6 header to send the ICMP message. We add the ICMP header as well, which ends up being an additional 48 octets. So we start with 1500, we add our 48 for the new IPv6 header and the ICMP. We end up with a new IPv6 packet, the new ICMP packet, which is 1548. We then add an Ethernet frame header to that. So we end up with a total frame size of 1562. The router on the left will then send that ICMP message back to the IPv6 trigger packet source. So it sends it from the left to the right. The router in the middle, because of mismatched MTUs or mismatched MRUs, says, hey, I'm being sent a 1562 octet frame, but I can only receive 1514s. Throws it away. And you never get retransmissions, because ICMP doesn't do that. It never makes back to the person who sent the original trigger packet, and it only happens for these bigger IPv6 trigger packets. A smaller one would fit through. The most typical symptom of this that you'll see is the giants counter. and normally it wouldn't be 0, except that I couldn't manufacture an example in time to have some non-zero values there. But that's where you see this. So this would be the interface on the router that's in the middle. It would be counting these as giants. Sometimes they also can be called oversized frames. And that's really, truly, the giant counter is one of the giveaways that you're having a mismatch. So this really means that to fully test MTUs and MRUs, if you're changing them, you need to ping in both directions across the link using full-sized or full MTU frames and packets. And if you get no loss in both directions at the full-size MTUs, you can be confident that the link does not have any MTU mismatch problems. Of course, you could just look at the parameters and look at the settings, and that's probably reasonable, but you then got to make sure it's not a host, it's not referring to different things. You know, two routers talking to the two routers connected to each other with the same MTU settings, same iOS, same hardware, probably all good. But to be truly confident, you need to ping. The trouble with ping itself, though, is that there's ambiguity as well into what payload it's referring to. So Cisco XR, for example, is referring to the full packet size to test with, including the IP header and the ICMP echo header. Hosts, however, it's been quite common for them to just be referring to the payload that you put in the ping packet. So it doesn't count the IP header and doesn't count the, or you're not counting the ICMP header. So you've got to do the maths and say, well, I want to test 1500, 20 bytes off for IPv4, 8 bytes off for ICMP, do a ping of 1472. Just more trouble. And it's also, for IPv4, good practice to set the DF bit so you don't end up sending packets that are too big out an interface that you can't send them. OSPF does an MTU check. In the database exchange packets, it will place the MTU of the outgoing interface to send to its neighbour. And if its neighbour then receives that, it will check against its own local MTU. If they don't match, the database exchange doesn't happen. So you do get a partial, I've forgotten the exact terminology, you do get the neighbours come up at the hello level, but the database exchange doesn't happen. So that's what OSPF does. ISIS goes one further. In its hello packets, it actually pads them out to test the link. So ISIS is more robust in this sense because it's not only checking, it's actually testing. The reason this is important to come up is because apparently it's possible to disable at least the OSPF check. I've been dealing with OSPF in various ways since 1995. I didn't know you could do that until about 2017 when I saw it done. Don't change it, don't disable it, fix the underlying problem. This is sort of, the Band-Aid of, sort of like you've got the engine check light on, just put a bit of black electrical tape over it and your problem's solved. So, don't turn these tests off. Go and look for the MTU mismatch problem. BGP. We all love BGP. BGP operates over TCP, so we need to understand how TCP handles MTUs and MRUs. TCP, when two neighbours come up, they exchange or announce a thing called the maximum segment size. The maximum segment size is really a very similar equivalent to an MRU, a maximum receive unit. So it's the TCP neighbour saying, here's the biggest amount of data I can accept from you. The trouble with TCP and MSS is that the values don't have to be the same, even when the MTUs match up. And that's because the MSS doesn't include TCP options, and a TCP peer can say, I want to use these options, and the other end says, I want to use this different set of options, selective acknowledgements, and forgotten others. So the point being is that you can have different MSSs, even though the link's got the same MTUs, but the trouble is because you can have different MSSs between peers, it can also hide MTU mismatches at the lower layers. If you want to dig deep enough on some operating systems, you can actually find it. I won't go into detail much, but here is an example of a Cisco OS device. If you dig deep enough, you can see at the bottom left, this is for a BGP connection between two routers, and there's the local MSS that would be announced to the neighbour of 1240, and the peer one has announced 1240. Given these were two Cisco ISXR routers, they are using the same options, which is why these values are matching up in this example. So we have our BGP connections established over a mismatched MTU scenario. BGP will come up. The keeper lives, which I must admit I'd forgotten until recently, BGP keeper lives to test the neighbours there are 19 bytes. They don't test the MTU. So the keeper lives will go and your BGP session will sit there running quite happily for hours and days until at 3 o'clock in the morning there's a BGP update that's big enough to trigger the MTU mismatch, and then I get called at 3 in the morning, like it was about 3 weeks ago. Actually, no, they called me at 6, but the problem had been at 3, and it was one of our 24/7 NOC people. I'm thinking, well, it was working all last night, and you're the only person complaining. Maybe it's your connection, not. But an hour later, it was everyone's. So a BGP session coming up is not a sign that MTUs are correct, sort of unlike OSPF and our ISS. So don't trust BGP to be doing, enforcing this or ensuring it. Use ping if you're going to change the defaults. Another thing which I need to cover here, and then we'll use it later, is what I call dumbbell MTUs. It's a bit extreme, but big, small, big scenario, or maybe a little bigger and small in the middle. But this is how I imagine it. Here's an example of a dumbbell MTU issue on a link. Hopefully it's pretty obvious what the problem is by now. The switch in the middle has a default Ethernet MTUs, or frame MTUs of 1514. For some reason or other, the routers on the ends have had their packet and frame MTUs bumped up a bit. This means that the routers can send to each other bigger packets than will fit through the switch. So you've got to get rid of your problems there, but that's a dumbbell MTU scenario. To cover these terms off, if you happen to see them, we're getting into the realms of the Ethernet specifics. We have a jumbo Ethernet frame. This terminology seems to have disappeared, but it's where it originally came from. They're about 9,000 octets. After that, a while later, mini jumbos showed up, and they're about 2,000 octets. The problem is that they're not standardised. The IEEE hasn't spec'd them. Which sort of goes to the question, well, are bigger Ethernet MTUs always better? And not always. Firstly, the IEEE haven't standardised them, and I heard that it's because they didn't consider that the checksum was strong enough to protect the data for these larger frame sizes. Admittedly, that was a choice when coax was the thing, so maybe we're getting away with it because of fibre these days. But there is no standard on these sizes, and that's the problem. You can't say, well, the jumbo size is always 9,000. Like we can say the standard Ethernet is always 1,500. And things just work with Ethernet defaults. I mean, I'm sort of surprised. The amount of trouble we're seeing today, I think, is because people don't fully understand what they're changing. I leave it defaults as much as I can. Sometimes there are benefits, and there's really two cases. One is for higher throughput, large file transfers to and from local network sources, and also to tunnel full-size packets and frames across the network. However, to understand that, we need to understand PMTUs, which are path MTUs. The path MTU, this is one of the RFCs that refers to discovery. The path MTU is basically the smallest MTU in the path that the packet's going to go through. In this example, we've got 4 routers, we've got 3 different MTUs on the links. We've got the default Ethernet one on the left, a 9K one in the middle, and a 2K one at the end. On the path from the far left router through to the far right, the path MTU is 1,500. On the router from the far right to the far left, sorry, to the middle left, the second left, the path MTU would be 1986. What's the internet's typical PMTU? Well, it's 1,500. The internet's all built of Ethernet today. So if you're going to use an internet connection or you're going to send stuff over the internet, don't waste your time with anything but the default Ethernets. You're just creating issues. Going back to our dumbbell example, PPOE creates a dumbbell scenario in terms of paths. So admittedly, I forgot to label the router types, but the router on the router next to the host is a customer CPE. The router adjacent to it is a BNG or BRAS or whatever you want to call it. Because of the overhead of adding PBP to Ethernet, the packet MTU on that link becomes 1492. And we get this big, small, big scenario. How to deal with dumbbell MTUs or PMTUs? Well, there's two methods, IP fragmentation and path MTU discovery. They're interrelated. That RFC I quoted earlier was the PMTUD one. Both of them have issues, and this is still a current issue that's ongoing with the internet protocols, because really we would like to use bigger MTUs across the internet, but we can't. There's a couple of papers there you can look up later, fragmentation considered harmful and fragmentation considered fragile, that go through these issues, and the second one's quite comprehensive and fairly recent. The takeaway, avoid IP fragmentation. And if you're running PPOE, there are ways you can get rid of your dumbbell PMTU. This is the RFC with the typo, the maximum transit unit in its title. But this is a way of increasing that MTU of that middle link up to 1500. So now you've eliminated your dumbbell scenario. They're doing it by going slightly oversized on the Ethernet frames. Before I worked for Aussie Broadband, I actually found that NZNOG supported this, and the NBN does too. So if you get the right CPE, you can start fiddling and try and get 1500 all the way through from home without the carrier knowing. Talking about tunnels, going too bad on time. Firstly, I think it's interesting to think about where tunnels fit in the internet architecture, because it answers some of the questions of what you have to care about. I've realised that the second sentence there, a tunnel provides a method to get a frame or packet somewhere else within a single hop. It's a bit confusing. I'm not talking about the tunnel underneath, I'm talking about the carried packet itself. To the carried packet itself, it looks like a single hop. That's what all of our links do. So that's where the tunnels fit in. They fit in below the IP layer. They're a virtual link. Our tunnel goals: carry packets or frames up to a certain defined maximum size without having to do tunnel packet fragmentation or getting loss, depending on the tunnel protocol we're using. A scenario, a simple IPv4 over IPv6 tunnel. Start with 1500 for our IPv4 packet. That's the maximum defined size we want to carry. We add our IPv6 header because that's our tunneling protocol. We're not going to add anything else. We can do native IPv4 and IPv6. We don't have to use GRE. So if we add those two together, we get 1540 octets. So we need to have a path MTU through our network of 1540 to avoid IPv6 fragmentation. If we then add Ethernet to that, or Ethernet overhead, we end up with an Ethernet frame running total of 1554. So that means all of our links in our network need to be able to carry Ethernet frames at their frame MTU. So on that 1514 on the Cisco router, it needs to be 1554 now. The real question is, would 1554 be okay? Well, definitely it would work and it'd be correct. But if you're going to change the MTUs throughout your network, you're probably better to allow for other tunneling protocols and other future uses. So you may as well go what I call averagely large. 9K, if you can do it, is fair. But the thing to remember is that because it's not standardised and there's different sizes for implementations, you might find one vendor supports 9200, another vendor supports 9186. You sort of got to try and, if you're going to go down that path, and I generally think it's fair, try and sort of pick a reasonably high value that can be used on all of your current and future devices. So in some regards, be a bit conservative. I used to put them up as big as they'd go, but yeah, so, 9,000 or something like it seems reasonable to me. So to avoid fragmentation in your network, including of tunnel packets, have a big enough MTUs to avoid triggering it. So, to the questions. Sorry, I've gone a bit of time, but I owe back for being quicker. To the questions. Number one, when shouldn't you change MTUs? When the Ethernet default MTU is good enough. Because then you avoid the risks of MTU mismatch problems, all the issues we've been discussing in this presentation. When should you change MTUs? When the benefits are worth all the costs. Or in other words, I don't change it unless I've got a very specific reason to, and then I have to dig into the worms of what MTU value I'm changing, etc., all these sorts of things. This presentation is a bit of work in progress. I've only written in the last few weeks. I do have a goal of sort of trying to make it more comprehensive and expansive, so it becomes probably more of a tutorial. I'm a bit inspired by Richard Steenberg's 1+ hour presentations on traceroute and optical, because I've been thinking about this topic for a while, and there's the list of topics I've come up with. We've touched on quite a number of them. There's quite a bit of depth that could go into some of the others, and I'm also looking for other suggestions of further topics. That's how you contact me if you've got some feedback, suggestions for areas to improve, other topics. I was having a chat to Rich from Arista yesterday, and he mentioned MTU's influence on policers and shapers and how they count layer 1, or what I would call the medium MTU. But I'm keen to, at least it's taken me many years to discover all these things. It'd be great to have one presentation that says, this is the story of all of this stuff. Thank you very much. Any questions? And that's my copy of the story of ping, by the way. It's got to be on my networking shelf.
So one thing you haven't mentioned is the cloud provider networks. And so the question, I guess, is you sort of recommend 9,000, and I think I see more problems inside of cloud provider networks these days, like Amazon and Azure, with people trying to put MVO networks into the VPCs or whatever they call them in their particular cloud, and then having a big data lake that they need to want to use jumbo frames on. 9,000 is not good, because you need to have Q&Q on top of that generally as well. So, thoughts?
Well, I'll qualify. In my general experience, 9004 is probably going to fit. But it's general experience. I mean, you know, I don't know what vendor Amazon are using. In some regards, I'm not recommending 9,000. I'm saying don't change these at all. But if you have to, these are the sorts of, the can of worms you're opening. But yeah, in other people's networks, it's sort of worse. This is where the path MTU stuff comes from. Yeah. And some of my concern in recent times is people not fully understanding the history of why these different things came along, so just make 1,500 everywhere, even though it's on a router, and therefore it breaks things, and so yeah.
A couple of observations from the layer 2 guy. There is a standard for larger frame sizes, that's 802.3 AS.
Oh, okay.
And basically what it says is, yes, your data MTU is 1,500, live with it, but your maximum frame size is 2,000. And that basically says when you're going to start adding layer 2 headers, Q headers, MPLS, all of those lovely things, you can go up to 2,000 for your total frame size. That's from the beginning of your Mac header up to and including the FCS.
Yep. Okay, that's good. I wasn't aware of that one.
The other thing, just as an operational thing, when I've built core networks, I've usually sort of set the frame size to whatever the hardware handles, but always set the IP MTUs at the standard 1,500 for management. Because
there's
otherwise your head just explodes.
There's a topic I've specifically ignored. You can actually have an Ethernet interface that can do bigger frames, and then you say, well, I want actually IPv6 to be limited to this. That's
well, again, if you're running at layer 2 networks, that's, you're offering payloads of up to over 9,000, 9,100 is a typical sort of what you offer, even though your hardware can do more than that. But you don't actually manage it at that stuff. So your layer 2 payload, you don't really care what's inside it.
That's another issue that I've also ignored, is the fact that what you offer the customer versus what your network supports, and it's a big mistake to say we offer what, you've got to allow for overhead that the customer doesn't see. But if you're naive and say, well, we do 9K frames, and then you find that you've got a 9008 and then you can't carry the, can of worms. Thank you.
Sorry, Mark. In your example with the unnoticed data loss, why would path MTU discovery not fragment the error message? Because you're coming back from a 1600 through a 1500 up to a 1514.
Because in IPv6 there's no fragmentation in the network.
But PMTUD should pick that up.
But well, the thing is that the router, the next hop router, won't even accept that frame because it's too big.
And you'll get a packet too big?
No, you won't. It won't accept it. It drops at the Ethernet layer.
Okay.
And also the other issue is that ICMP can't trigger another ICMP message.
I haven't tried it.
Yeah, no, it's against, because you realise that you could potentially get errors triggering errors and an endless creation of...
Wonderful.
Yeah, ICMP, rate limited, not reliable.
Right, thanks.
Oh yeah, g'day. One of the things that I loved about this chat is it hits very close to home because I've been dealing with the same issue. And I went down the rabbit hole and tried to figure out something. Why 9K? Why did we as an industry all settle that 9K is it? And the only thing I've found is a Cisco Catalyst 6500 white paper showing that that's what they settled on eventually, and we all just kind of adopted it.
I don't know why the 9K. The only thing I do remember about it is I think there was a networking company called Altion.
Yeah.
And they invented the first network cards that would do 9K. And I think they were 1 gig cards. It all sort of, all these problems mostly arose after 1 gig and VLAN tagging.
Yeah.
Before all that time, you didn't change it because you couldn't, and it worked.
Yeah, thanks.
With my Amazon hat on, since I'm in the room, if you're trying to get packets into AWS over Direct Connect, you can get either 1500, this is the frame payload MTU, 1500, 8500, or 9001, depending on various settings and topologies.
Yep, cool, thank you.
Looks like that's it for questions. Thank you, Mark.
Very much.
So just actually, before we start the next talk, just a reminder to mute your cell phones and laptops. There's been a lot of kind of noise coming from the audience, but distracting to speakers. But next up, we've got Noel Thompson from Arista, and he's here to talk about AI and AI ops. Thank you, Noel.
Morning, everyone. How was that meal last night? Pretty good, eh? Yeah, some of us, after I ate, I was so sleepy, I just wanted to go and sleep, too much meat. But yes, I'm Noel Thompson. I'm from Arista Networks. I've been there for 3 years now. I know a lot of you around the traps, working at different vendors or different service provider companies, etc. So when I asked Nathan if I could present at NZNOG, I suggested this idea, and he immediately said to me, "Oh, Arista does that." Yeah, but so do all the other vendors in some sort of way and form. But I'm going to take sort of a holistic view for you guys. I'm going to cover it from a high level, and then, yes, take away what you want and take away what you don't want. Okay. So, just some questions that, ask yourself through the presentation. Like, what is it? Sort of look at it from your perspective, from your viewpoint, okay? How will it impact you, yourself, your organization, the people you work for and the people around you, and sort of how to get started with AI and AI ops. Okay, a bit of trivia. Who knows what this is? Yes, you can see all the formerly older gentlemen in the crowds putting up their hands, all the younger people scratching their heads going, Skynet? Yes, it's the machines. Okay. Sort of in our era when this movie came out, this was the introduction to the machine taking over the world. Skynet, self-aware, self-doing, self-killing everyone. Okay. Yes, we're not going down this path, and hopefully we don't ever get to go down this path. You know, the iterations of the movie was 1 to 25, I think, or something, going from a metal form factor to a liquid to a nano to I don't know what, but hopefully we don't get there. Just to cover off, what is AI, okay? I went onto the internet as usual. What is AI? Man, too much information bashing me in my face. So I took the most simplest form. Okay, AI is the ability for a computer or machine to perform tasks. Perform tasks is probably the key factor here, okay? Yes, we input information into it, we give it information that has data, and then it takes that data and it learns from it, okay? It can be any data. There was a word that I found called multimodal data, okay? It's pretty much anything that you can give something so it can learn from it, create from it, etc., okay? AI can be trained, that's machine learning. And from a machine learning perspective, man, that's another very big kettle of fish, all right? Data scientists are into it, people are looking into it, people are trying to find ways to create all these sort of algorithms and stuff set against data so that you can extract information from it. And the more information you feed it, the more information it learns and grows and detects, okay? Machine learning is, yeah, you know, supervised, unsupervised. Understanding, you know, where you can apply this and how you apply it is, I think, is the best way to go forward. So I was thinking, while I was showering this morning, I was thinking, how can I put in an analogy to AI, machine learning? We do it all the time as human beings, okay? So we are constantly learning and evolving, okay? We're given a certain task to do. We have information around that task. We do the task a specific way, but no, we're smarter. We start learning, changing how we do that task to make it better, more efficient, more faster, okay? Now, from that perspective, the only element that's different to everything else is we are our own intelligence. We can think for ourselves in many different planes, okay? So this is how we need to educate the machines and et cetera to be able to make those decisions and those tasks. All right. AI every day. We're all using it all the time. It's around us. In our phones, in our TVs, in our laptops, whatever do we speak on the phone. This artificial intelligence has been built into us or built into our lives, environments all the time, okay? People are using it to be able to make decisions for us, unfortunately, okay? Some of us are smarter and we don't answer that specific call that comes in from Australia. It's always Australia. If you get those calls, those dodgy phone calls. So the whole concept of using AI in AI ops into networks and stuff is to take that fundamental idea of AIOps and use it in our environment. I say our environment because we're all network operators, we work in this industry, and we know what the pain is. So the nirvana, self-healing, self-driving, you know, the automation, predictive fault analysis. That's where we want to get to one day with this, with the AI ops and that. But it's a journey to get there. You know, it's not something that will happen overnight. It's just something that we need to sort of start thinking about because it is the future. All right. So, just another point on that. No, we won't lose our jobs. We won't get fired. We won't be asked to move away. Using AI and AI still needs human input. We still need the network operators. We still need the network designers, the architects. There are people working on the applications, etc. So from that principle, we should say we should embrace this, but embrace it in a way not know we're going to get kicked out at the end of the day by a metal man. Boom, one of them. Okay. So, ChatGPT. Everybody, it's been mentioned a few times here. Beck used it in his presentation. It's been referenced. If you don't know what it is, you've been living under a rock. Okay. I thought I'll just cover off because this is the latest hype. Everybody's using it. Everybody's talking about it. Okay. It's an application from OpenAI. It's come out in different iterations, formats. It's getting better. A lot of the time you go on it, it's down because 52 billion people are trying to use it. Okay. So what it is, it's a generative pre-trained transformer. So that's some sort of AI language that they use to train this. Okay. The biggest thing from ChatGPT, you use it, cross-reference your information. Okay. Because the information that it gets, it scrapes it from various sources, and that information doesn't always seem to be correct. A lot of the time it is. My son who's in the last year of school, I introduced him to ChatGPT. Man, just loved it. I said, don't use it, cross-reference your information. So he does, and he's found a lot of mistakes, which is relevant. So I'm going to go into a quick demo on ChatGPT. Hopefully you can see that I try to make it bigger, but my big and your big is different because I'm half blind. So I took ChatGPT. Essentially what we're going to do is get ChatGPT to configure 2 switches, ping across it, and configure BGP. Okay? Of course I use the rest of the switches. Why not? But it's just the way you ask the question to ChatGPT and how it interprets it. Okay? Because if you ask it in a different way, it won't do it for you. So it's very specific on how you ask it its questions. All right. I hope this works. So I think I'll just focus on the first instance at the top. Okay? I asked it, I gave it a specific instruction, and then I said, within this instruction, I'll ask you other instructions, but I'll frame them in curly brackets. Okay. And then it went away, and it built it. So that's just doing a show version from the first side, and then I asked it to configure an Ethernet switch and then connect it on Ethernet 1, and it went away, and it just used arbitrary IP addressing, and then the interfaces came up. Then I asked it ping between the interfaces. There we go. It's always good when we see the result like that. Yes. And then I say go and enable BGP on this, and it went and configure BGP between the 2 switches. And then I just said show IP BGP summary. So a tool like this can take what we often, look, a lot of us can do it in our sleep, all right? But you take somebody new coming into the industry and they can use this tool to do what we've been doing all our lives and do it in a second like that. Yes, it's great, but do they understand what they're doing is the key factor here, all right? I just thought I'd show you guys, if you don't know ChatGPT, go and get it. So just some trends that are happening in our industry now, okay? Of course, AI and ML. I think the key thing there is taking AI and ML, using it on our networks now where we can, where it's applicable, and what will give us the best advantage, all right? SDN intent, SDN and networking intent, all right? We're doing the network automation thing, central orchestration, management, but it's going probably to the next step. Open automation pipelines within the network, CI/CD, okay, and then pre-deployment testing before you start deploying networks. And then, of course, network observability, I think, is quite a big one, all right? Lots of network data collection points within the network. This causes, fractured storage, etc. It's just bringing all that information together into one common storage location, and then this will help us just get a composite view. So you can see I built this slide from an engineering perspective. So this is what problem we're trying to solve. We've all been here, okay? You've got your infrastructure, you've got your applications, you've got your network, you've got your security cloud coming in, all sending information into the network monitoring systems. Each one's got its own management domain. Each one is trying to do its own thing. Johnny sits next to Daryl, but Daryl works in applications, Johnny in networks. They have no idea what they're doing, okay? All this information gets streamed into a NOC. So there's a fault on the network. What is the fault? Where is the fault occurring? What is it happening? It just causes stress. Longer time to resolution. No cross-domain communication. One blames the other. One says it's not the network, but it's always the firewall. It's always the firewall. Okay. I put that in red as a bit of a tongue-in-cheek. When I was working at one of the service providers, it was always the firewall. Okay. Multiple alarms for one incident, and then obviously you have the management breathing down your neck. They don't know what's going on. They're trying to understand the position. Okay. So this is just a very poignant view of what's happening in terms of the situation we're trying to solve. All right. It's a very busy slide, but sort of this frames up the picture. Okay. AI ops. All right, now we just take a step up and we look at it from an automation, machine learning perspective. So integrating analytics, automation, and optimization into a single platform, getting all the information ingested into one location. All right? Now, what is the outcome of this? To help drive a faster root cause analysis and then accelerate mean time to repair. Taking all that information reduces noise reduction, event correlation, and then obviously the machine learning aspect, okay? Putting the machine learning onto there to be able to analyze, predict, and spit out the relevant information to the user side to be able to make decisions. Now this could be across all the applications, servers, firewalls, etc. And then at the resolution side of this is for us to be able to get to, better collaboration, notification, known remediation, etc. And just help with the incident management. And if there's any automation on the back end of this, we can do that. Okay. So make sure I don't run over time and keep you guys out of your lunch or your break. So essentially what is needed for this nirvana where we're moving to. All right, we have, the most common thing is data, information. Where do we store it? How do we store it? A lot of vendors at the moment are doing this, some sort of AI. It's very prevalent in the campus and the Wi-Fi space. There's a lot of this information being ingested into repositories, and AI and machine learning has been done on this data to be able to give relevant outcomes to the customer. It's not a new thing, okay? But it's just how do we expand this across all facets of the network, all right? So you get data source coming in from customer A, it's relevant to that customer. Big data, yes, it's really good. But now taking multiple customers' information and chucking it into a big data lake. Okay, I'm using data lake because it's a very common industry term, where you have petascale of information, of users' information inside this lake, customer A, B, C, D, E, F. And the AI and the ML can analyze all the data across all customers instead of just one portion. So the more data it has, the more it can think about it. Essentially, a data lake is just a logically centralized repository. So you can have a massive data lake across the world, but it's all one but dispersed, for example, okay? It's layered, loosely coupled, data sets. It's governed under, one control. And the data lake essentially is storage, tools, and services. Now, on a data lake, why is it important to have a data lake? All right? It's a key enabler for AI ML, all right? The multimodal data, this is all data that it can collect, all right? And this will be able to give us insights and predictive outcomes. Now, the multimodal and multi-tenant network-centric data lakes enables ML applications, third-party ecosystems ingesting information into it to unlock, the value out of the data. And of course, we can all be smart. We can stick virtual assistants on the top that can help users analyze and predict or use this data for troubleshooting purposes, etc. All right. So just third-party ecosystems. So we have our data lake at the bottom, all facets of the data lake, systems, internet, identity, etc. Okay? This is managed by an AI ML enriched engine, and we have third-party ecosystems ingesting information into this data lake. Now, this is all done through an API interface, of course. Obviously, there needs to be a partnership between your data lake and the ecosystems to be able to ingest this in. But a lot of these industries, a lot of these partners have open APIs for us to be able to exchange information between. Okay? Then we have a network, the network ecosystem, of course, everything. Public cloud, campus, branch, internet, data center. Ingesting information into the data lake, how it's done via telemetry, SNMP, x86 sensors, your security sensors, all just pumping this information into the data lake. And then the outcome of it essentially is you get, prescriptive insights as to what's happening on your network. So the outcome of the machine learning and the digital or the information from the third-party systems and the network, you'll be able to anomalize certain areas of your network. The DRs, that's the new buzzword, detection and response. Autonomous threat hunting, APM, etc. Okay? So from this, I've highlighted two areas where, I can highlight the fact how AI and ML will be able to assist us, to be able to analyze and predict something that's going to happen in the network and do the relevant notification. So component failure. I guess the information that you get from the component is very static. It's very relevant to that component. If there's any slight change in that component, obviously there's either a defect in the component or the line, all right? So having all this information, telemetry information streamed into the cloud, you have your AI engine working over the top of it. It notices something changes within the current or the temperature, etc. And then there's a degradation in the signal, for example. Then AI can say, okay, this link it's not 100%. It could predict that it's going to go down under a certain period. And if it does go down, obviously there's going to be an outage. We can preemptively, get new optics to the client via some sort of mean, via TAC or direct contact. And then the customer can put in the new optics and obviously get that link into its 100% state. Okay, so that's one side of it. And on the other side, our famous TAC organizations. Everybody loves TAC. So everybody goes to TAC for everything. Oh, how do you configure an IP address on the interface? Phone TAC. All right. So this has sort of become the central repository for everything, or all information. Understanding that it's the central point where, you know, if they have visibility of everything in the network for all customers, it depends on what they're doing, they'll be able to make the relative decisions, okay? Currently we have self-TAC. If I say we, talking in general about organizations, you know, you have your TAC forums, you have your chat groups, your community lists, articles and designs on the web pages and stuff. So all that information people use, all right? Now you go one level further, all right? Having obviously guided insights, using intelligent tools on the information, TAC information coming in, cases get logged on certain parameters, certain features across multiple people. Now, if you have an AI, ML engine across this, all that information gets correlated, and the TAC engineer doesn't have to spend 25 hours looking at a case, the resolution will be a lot quicker. Okay. So, I guess looking at this model, it's speed to resolution, all right? Productive engagement and faster response, proactive detection, not reactive detention of issues and mitigations, and then obviously all the knowledge that gets collected over time just uses that for faster resolution, reduce MTTD, time to detect, and time to repair. Okay. So the end result. We have the network always working, like us, of course, we're always working, always watching, always gathering, and also like us, I guess, always evolving. But this will happen with guidance from us as people inputting into this. So, yeah, that was just a very high-level 360-degree view. And please don't be scared of the machine. It can be killed, so at the end of the day, you know, it's just for us to embrace this and to guide us through this, you know, to the next generation of our industry. So, thank you for listening, and enjoy the rest of your day. Thank you. Questions? No?
Any questions from anyone?
Better not be hard.
This is more of a question about your roadmap. So Microsoft's going to release Copilot soon, which is ChatGPT embedded into its applications. Are you going to release something embedded into the CLI for Arista products that you can say, please configure BGP?
I can neither confirm or deny.
Thanks for the talk. So in network, we have, in machine learning, we have two types of data, numeric and categorical data. For example, interface statistics, system uptime, graph, even image processing, all of them are sort of numerical data. So for the image processing, we have multi-dimensional matrix. So what do we do for the categorical data, like IP address, or as you mentioned, the syslog. So syslog is is not a number, so we can't learn the deep learning or these things. Yeah, that is the question.
So I just think in that concept, I think it's a lot of it is about real-time telemetry, all right? And the consistency is getting the data when it originates from the switch, not third-hand data that's 15 minutes late. I don't know if that's going to answer your question. So I guess with that information, we receive it immediately within, the engine. Once we receive it within the engine, if there's any anomaly or changes or anything that's different, then you can categorize that as a change or as an anomaly or as a fault. I don't know if I've answered your question correctly there. Yeah, come have a chat to me, all right. Yeah. No one else? Enjoy your coffee. Thank you.
Cool, thanks Noel. So we're going to kick off again at 11 o'clock, so you've got about a 25-minute break. If you're feeling a bit weary from all the food last night, then there's Searchlight Coffee at the break, so get some of that into you. Anyway, see you back in 30 minutes, 11 o'clock. Cheers.
Okay. Hello? Okay, let's get started. We're up to switch giveaway time again. It's going to be a little bit harder to find people in the audience, possibly. Is Josh Atkinson here? From Spark? Josh? No? Okay, going. The next one number I had was 3. Taylor Green from Primo. Okay, the first speaker in this session is Shane, and Shane's going to be talking about some work I think you're doing at Georgia Tech. So.
All right, hi, my name is Shane, and at the moment I work for myself. So what I'm going to be giving you a little talk on is about the many varied and exciting ways that the internet will stop working. So some of you may recognize me from various talks that I give about OpenLI. This is not a talk about OpenLI, that's coming up very shortly. But this is instead a talk about work that I do as my other hustle, where I'm essentially a freelance internet measurer. I'm taking the skills and experience that I gained working for WAND over many years, and now I make them available to other research groups, organizations, anyone who kind of wants someone to come along and help them with building and maintaining measurement platforms so that they can go and do some like science or learn something about their networks. So my main clientele at the moment are academic research groups, and in particular, the client whose work I'm talking about today is the Internet Intelligence Lab at the Georgia Institute of Technology. This was founded in 2021 by Alberto Dainotti. He was formerly a research scientist at CADA over at UCSD, and then he took up a professor role at Georgia Tech and started up this lab and invited me to join him. So the lab's focus is mostly on using internet measurements to understand the security and the reliability of the internet, and in particular trying to focus on the types of real-world events and relationships that influence the stability of the internet. Trying to sort of detect these situations and document them and classify them. So it's a relatively small team, but it is growing quite quickly. So we've got 4 academics who drive the science output of the lab, a bunch of students, both postgrad and undergrad, and then there's kind of me in the middle who actually does all the hard work. So there are 3 main projects that the lab's working on. The one I'm going to be talking about today is Internet Outage Detection and Analysis, or IOTA. There are a couple other projects. There's the GRIP project, which is focused on detecting BGP hijacks. I was hoping to talk about this, but I just didn't have room in my talk to fit it in. And then finally, there's also MapKit, which is a project to try and identify vulnerable points in the internet topology. I don't have much to do with that one, so I won't be talking about that at all. Right, so let's talk a little bit about internet outages. So the first thing I want to clarify is that today I'm going to be focusing on what we call macroscopic outages. In other words, outages that basically will take out an entire geographic region or an entire network, right? We're not talking about what we call microscopic outages, where, say, a roadside cabinet has fallen over and a neighborhood's been taken out, or a small subset of your customers. So what are some of the causes of internet outages? Well, one that we should all be familiar with is damage to fiber optic cables, because that seems to happen pretty much every other week around here. Of course, we're all very smart network engineers, and we understand the value of redundancy, and so a single rogue backhoe or excavator is not going to necessarily lead to an outage, but there are some cables, particularly some ones that are under the sea, that are essentially the only point of access to particular regions. And if those cables are damaged, such as if a volcanic eruption over in Tonga happens to take place, for example, then that entire area is going to go offline for some time. Weather events. I don't know if you are familiar with how a weather event can affect internet connectivity, but they definitely can. Hurricanes, cyclones, typhoons, all of those tend to leave network outages in their wake. The big factor here is mostly that they tend to affect the electricity grid and take that out, which will, regardless of how well protected the core of your network is, right? You've got a nice sturdy data center, you've got generators, backup, all that sort of thing. That doesn't help too much if all of your users at the edge have lost power at their homes. So it still creates an outage in that case. The other thing to consider, of course, is that radio towers and other remote network infrastructure can also be damaged as a result of a weather event or a natural disaster. Internet blackouts. So these are situations where authoritarian governments, when faced with some amount of civil unrest, will simply shut off the internet to prevent the protesters from communicating and organising and to try and regain control of the situation. The other motivation for an internet blackout would be to prevent any live streaming of any particularly violent counter-protest activities and just try and sweep the whole thing under the rug until the world forgets about it, at which point they can then restore the internet. Internet blackouts can take a few different forms. So they can range from just a complete total blackout of all internet services to the blackout for very specific providers, particularly mobile providers, all the way down to creating an outage for very specific services like social media and messaging apps. Generally, which form of blackout will take place depends on A, how much control the government has over the operators, and usually that's quite a lot, but also how obvious they want the blackout to be to independent observers in the outside world. Human conflict, unfortunately, as we heard yesterday from Rene, can lead to quite a lot of disruption of internet connectivity, particularly the result of damage to infrastructure by shelling, but also operators just being forced to leave conflict zones and not being able to maintain the network anymore. Attacks in cyberspace can be equally effective at causing an internet outage, so a poorly mitigated DDoS or ransomware attack is going to certainly affect a network's users. And then finally, there's just the case where things go wrong at the operational level. Some bad config, a vendor bug, something like that is all just as likely to lead to an outage for your users. And a particularly notable example of that would have been the Vocus outage in 2021 that Simon spoke about last year. Right, so now that we know what causes outages, how do we go about detecting them? So the way that we do it in IOTA is relatively simple. So what we do is we collect a bunch of time series of different metrics that we have decided we can use to infer the connectivity for a region or an AS, right? And then we break down these metrics by region, AS, country, and then use anomaly detection algorithms on those time series to try and spot notable drops in these metrics, which we would then infer to mean connectivity dropped off, right? Ideally, we try to do this in as near to real time as the measurement techniques will allow us to do it, because obviously it's more useful to be able to alert on the outage as it's happening rather than after the fact. We take all this data, we put it on a website for anyone to look at, and plot nice overlays on it for the events that we've detected, and try to correlate those events back to real-world events as much as we can and announce those via our social media channels. Right, so we have 4 different data sources that we use at the moment. Each of them has their own sort of strengths and weaknesses, but together they give us a good coverage of the different types of outages that we're looking for. So the first one is the BGP data. So what we do is we collate public BGP announcements from the RightBriz and RouteViews projects to give us sort of a 5-minutely view of the global routing table for the world. And then what we do with that view is we go through and we count the number of /24s that are visible for each country, region, AS, by at least 50% of the peers that are reporting to those route collection projects, right? So these create fairly stable time series because people aren't turning BGP on and off on a regular basis. So it makes it quite easy for us to spot anomalies. But the key downside with the BGP data is that obviously we're only monitoring whether the core of the network is up or not. It doesn't give us any visibility into the edge. So here's a typical BGP series over the course of a week. This is for the Auckland region. I've taken this graph straight from the IOTA website. And the important thing to note here, I don't know if you can actually see that. Do I have a point? Oh, no, I pushed the wrong button. Ooh. Got a bit fat-fingered there. That one. You'll see that the scale is actually like 99.5% down there at the bottom, right? So there is actually very little variation in the signal over time. Right, active probing. So This is a technique where we have a couple of machines that are just continuously active probing the internet using ICMP echo requests. And we use this particular method called the trinocular method. It's designed to be relatively efficient and a lot less annoying than typical scanning methods, so people don't block us. And we do these probing rounds about every 10 minutes or so. So what we do with the active probing data is we then count the number of /24 blocks that respond to our probes, and again break down country, region, AS. The data gets a bit noisier than BGP, but overall the trend is quite stable, so a lot of our basic anomaly detection algorithms still work on it. There's a slight underlying diurnal pattern because some people turn their machines off at night and stuff like that. But the important thing is that this gives us a lot better coverage of the network edge because we end up sending a lot of probes to people's home devices. So that's the same Auckland signal time period, but that's the active probing data. So you can see that slight up-down pattern in there, but it's mostly pretty stable. Anything above sort of 94–95% of machines responding to active probes is normal. If we start getting much below that, then we might think there could be an outage. The network telescope, this is a bit more of a different approach. So what a telescope is essentially a big block or a collection of blocks of unused IPv4 address space. Yes, those things do still exist. And what we're using the one from the Orion team at Merit. So there's a passive tap in front of this dark address space, right? And so we just they collect that traffic, and then we go ahead and analyze it. It's about 10 gigabytes of traffic per hour. And all of it is just unsolicited internet trash traffic, right? It's scans, it's background radiation, it's viruses trying to spread themselves to random parts of the internet. So what we then do is looking at the source IP addresses of the traffic that appears at the telescope, we again break it down by country, region, AS, and if we think that there's a lot of traffic that used to be coming from a particular region or network and now it's not, maybe that something's gone wrong with that network or region. We have to do a little bit of work here just to make the signal a bit more usable, because obviously there's a lot of extra issues with it. So we have to remove any traffic that looks like it comes from an obviously spoofed address, because that's going to mess with our numbers. And we've got a bunch of heuristics that we derived from previous work looking at spoofed traffic. The other thing we do is we remove particular types of traffic that we believe to be erratic. So things like common DOS attack vectors, ports that are often scanned horizontally, so they tend to be quite bursty and noisy. So we remove all of that kind of stuff as well. So we end up with a signal that's quite strongly diurnal, but it's not very representative of when it comes to the smaller networks and the smaller regions with less population. You'll see what I mean on the coming slide. So there's the telescope signal for Auckland. A bit noisy, but you can see a very clear diurnal pattern there. That's the telescope signal for the Bay of Plenty region. And you can see with those very marked steps between points that the telescope must only really be seeing a very small number of unique source IP addresses from what it thinks of the Bay of Plenty region. So this is a really hard signal for us to work with from an anomaly detection perspective. The last data source is the Google Transparency Report. I don't know if you've heard of this. This is a really cool public data set and API that's provided by Google that essentially gives you visibility into the amount of traffic that each Google service sees from each country. The interesting thing about this is obviously Google isn't going to tell you the number of bytes or the number of connections or whatever that they see, because that's commercially confidential information. So what they do is they normalize the crap out of that data, and what you get is effectively like a stock market index or something like that. The values are useful relative to the values that have been previously reported. So you can see, is the traffic for this service going up or down or dropping off or disappearing entirely? One of the downsides with the Google data is that they only report these values for 30-minute intervals, and there's about a 2-hour or so time lag before those values actually appear in the API. So it's not that great for detecting outages promptly, but it's really good for giving us some correlating information when we're looking at the outages retrospectively. So here's the Google Transparency Report signal for New Zealand. We can't do it at a regional level, as I said, but this is the New Zealand one. And you see very strong diurnal pattern, and also quite a difference between the, oh, wrong button, the weekdays, which are these 5, and then the weekends here. So this is a signal, sorry, for the search traffic. So during the week, people do a lot of searches in the morning, early afternoon. On the weekend, they sleep in, or they don't have questions that they need answered. So as I said, this stuff is all up on a website. You can go to that URL and take a look at it. There's a ton of different visualizations as well there. Fortunately, I don't have time to do a live demo because we're going to look at some outages. So this is the first one. This is Syria from the first week of June last year. And you can see there's a couple of very prominent outages there. Does anyone want to take a guess as to what might have caused those outages over in Syria? Of course not. It was exam time. The government shuts off the internet in Syria when the high school exams are on. The entire internet turned off. So they can't cheat. And this is common in that part of the world. Other Middle Eastern countries, North Africa, they do that. So can you imagine that? All right, here's another one. This is the Tehran region in Iran in September 2022, so last year. Anyone with a decent amount of current events knowledge might be able to guess what was happening in Iran at about that time. Sorry? Yeah, no, not. This was the Iranian government blacking out the internet because people were protesting after the death of Mahsa Amini. If you go back to that graph, you can see that there's some quite regular. So this first one, the big one, that would have been, oh crap, we need to regain control. These regular ones after that, those are outages over the course of the evening. So people get home from work, head out to protest, and effectively there's an internet curfew. You'll notice that we're detecting the outage, these little dips in the green BGP line. I'm not 100% sure, but I suspect that's them turning the mobile providers specifically off, right? So everyone's internet at home stays up, but if you are out and about and trying to get involved in a protest, then you are going to lose all communications. This one's really cool because this is kind of a 2-for-1 deal. So this is Cuba at about that same time of year. So we've got 2 different types of outages here. We have the big red circle one, and then we have these very obvious dips here later. So the first one, Cuba was hit by a hurricane, Hurricane Ian, basically wiped out their entire power grid, which of course created an outage. But the second lot is something different. It turns out that the Cuban people were not too happy with the government's response to both the hurricane and the COVID-19 pandemic in general, and they kind of had enough and started protesting, so the government shut the internet off again. So you can actually see that the government shutdown created a much bigger outage than anything that the hurricane did. And there you go. This one, this is the Kherson region in southern Ukraine, starting from mid-February last year through the month of March. I think we all know what happened in that part of the world during that time, and you can sort of see how as conflict intensifies, the internet connectivity gets more and more disrupted. Around March the 2nd, which is about there, officially the city of Kherson was occupied by the Russians. Occupation doesn't help, it makes things worse. This last one, this one's a little bit more obscure. This is the small African country of Djibouti on June the 7th last year, and there's a little 4-hour outage there where a lot of their networks seem to have dropped off the internet. This this was a cable cut. This was the Asia-Africa-Europe 1 cable was damaged, and it turns out that a lot of the providers in Djibouti and many other countries were quite heavily reliant on that cable. And so, cable cut, they all disappear. Fortunately, the damage occurred on one of the land-based portions of the cable, which is why they were able to fix it so quickly. If it had been submarine, then they would have had a much bigger problem. All right, so here's the part that you've all been waiting for. What happened during Cyclone Gabrielle, and did we see it on our graphs? Yes, to an extent. So here's the Gisborne region, and you can see a pretty clear drop-off happening during the time that Gabrielle was hitting. Here's the Hawke's Bay, a little bit of a drop-off, not quite so much firing on our event detection system, but yeah, we definitely see it. Now, you're probably looking at this, right, and you're thinking, come on, right? Come on, Shane. It was way worse than that, right? We've seen the pictures of what was happening with the fibre. We heard about how the power was completely out. Are you seriously telling me that 80% of networks were still able to respond to your active probes? I'd say you're right, right? Unfortunately, geolocation, which is what we're relying on here, regional level geolocation for New Zealand in particular, is very inexact, right? It just doesn't work. And it's all the providers we've looked at so far, they just get it wrong. And the reason is because you people don't structure your networks in a way that makes sense for that to happen, right? You don't go, oh, here's my IP range that I'm going to set aside for Canterbury, and here's the one I'm going to set aside for Bay of Plenty, right? And so what the geolocators do is they just go and look up the whois data for your prefix, and they look at where's your head office located, and they say, that's where all of your IPs must be. So that might work if you're a very small regional provider, but everyone else kind of just gets lumped into Auckland or maybe Wellington. So a lot of those Hawke's Bay addresses or prefixes that we were measuring were probably not located in the Hawke's Bay at all, and vice versa. On the other hand, our other breakdowns didn't work too badly. So this is the graph for Lightwire during that same period. And those of you who don't know, Lightwire, predominantly rural wireless in the Waikato and Bay of Plenty. So during the period where those regions were being hit, we see a fairly significant drop-off in the number of users that are still connected. I've spoken to some of the Lightwire guys, and they assure me that that's just power going out at the customer premises, and that nothing went wrong with anything they were doing. And then here's New Zealand as a whole, and you can see just there's that little bit of a 5% or so dip in our active probing results. So we were able to see it, right? Even though most of the rest of the country was able to stay up, it was enough to be visible on the graph, not enough to trigger an alert in our alert detection system. Just everyone else managed to stay up enough for that, but yeah, it was visible. So we've got a little bit of ongoing work as well, always looking to add more data sources, both the third-party ones. I'm working on integrating in a new active probing technique that's a bit more heavyweight, but it's also targeted at specific regions that we're interested in, places where there's lots of shutdowns and other things like that. Better event detection, again, I've been working on adding some seasonal AREMA-based forecasting techniques that will be much better able to handle those series that have those strong diurnal and seasonal patterns. So that's about to come online very, very soon as well. We've got a team of students, both design students and web developers who are working on a UI to fix up some of the glitches and make it all very nice. And then one of the big research activities that I'm going to be involved in the coming year is adding some support for techniques that can detect throttling activity, which is a technique that the authoritarian governments are starting to use a bit more to avoid detection from people like us that they're blacking out the internet. They just make the internet really, really slow. So things like active probes will still succeed, but the internet's practically unusable for the people on the ground. So that's all I have today. I'm happy to take questions if we have time, but yeah, feel free to check out the site and let me know what you think.
Any questions for Shane? Nope. Okay, thank you very much.
Thank you.
Right, so next we have Dean and James from Cassini, is that right? Yep, to entering the cyber realm, so over to you guys.
Do you want to drive this? Yeah, I can drive this. Yeah, I'm going to drive.
Cool. Hi everyone, I'm James. This is my first NZNOG. Many of you will know Dean. This is not his first NZNOG. And we're from Cassini, here to talk about our experiences over sort of the last 3 years or so doing disruption using malicious network indicators. So what are we going to cover? Very briefly, what we do, just going to give you a bit of context so that you can understand the data that we're going to present. We're going to answer whether or not we actually have enough data to be relevant. What sort of attacks we see, a bit more detail about the data, how the IOCs behave over that time, and a little bit of case study and some interesting bits and pieces at the end. Danger, Will Robinson. The next slide could be interpreted as marketing material. It's just to give you a bit of context on how the service works. So we provide a SaaS service. We take threat indicators from a couple of government feeds and we task those into our customer networks using sort of config level integrations to things like firewalls, routers, DNS solutions, EDR solutions like Microsoft Defender, where they get disrupted, and then we pull telemetry back out of those networks using a variety of integrations, things like syslog and REST API hooks and things like that, and we give our customers some nice graphs and things in the SaaS and provide that information, a subset of that information back to the feed providers. So do we see a statistically relevant portion of disruptions? And the answer is yes, yes, we definitely do.
Yep. Anyone who wants to know more about that can come and see us at lunch.
So that's the end of the context, and hopefully that will sort of give you a bit of a frame to use when we're talking about the data coming up. So, what sorts of events do we see? What sort of disruption activity do we see? It's a fairly busy slide.
Grab the big button on top.
The red button on top. Right. That one? Yep. Yeah, cool. All right, if I can, there it is. I'm colourblind, so the red dot is quite hard for me to see. The lines on this graph represent the number of packets, so the amount of data that's or actually the number of disruptions, sorry. So here we're seeing a single source attacking a single destination, and as you can see from the thickness of the line, very, very high volume of traffic going on there. Next one down, a small number of sources reaching out to a couple of customer endpoints, and then some different variations sort of on the next few down where we've got maybe a small range of source IPs going across pretty much our entire customer range and various flavours of that as we go down.
No, forward. Yep.
Some are a little bit more complex to sort of understand. So what we can sort of discern from this view is that we've got multiple sources reaching out to just a couple of customers primarily, but based on the fact that all of these lines are really evenly distributed, we can infer that the actor in this particular case is using some relatively sophisticated load balancing, and they're distributing their load very evenly across their attack targets. and sometimes just everyone's having a bad day at the same time. So a little bit more about the specific data. We have 3 types of IOCs that we task. So there are URLs, domain names, and IP addresses. That's what the feed providers have. This is a little bit of information about the indicators. So we ingested our first production indicator in May 2020. So far we've had just over 100,000 indicators go through the system. But interestingly, just under 4% of those indicators have seen sightings. So a large number of the indicators never get hit, or at least never get hit by our customers. We do know that different organisations see different attacks. So it could be that there's a slightly different distribution from other people, but yeah, it's only a very small number of the indicators that actually get hit. And there's a bit of a breakdown in the graph too by category where that's possible. So we can see that the category breakdown down the bottom there. What time of day are the feed providers publishing indicators? Around the clock. So there's a bit of a bump during New Zealand working hours, as you would expect. But they do come in round the clock. And there was an interesting takeout in the latest NCSC report, in that they continue to see an increase in the speed and scale at which actors are exploiting vulnerabilities. And that was really evidenced by a recent Fortinet vulnerability. So Shadow Server said that they were seeing exploitations of that vulnerability the same day the proof of concept exploit was made public. So you really need to be tasking the indicators immediately, because the actors are just moving so quickly now. In terms of telemetry, we got our first piece of telemetry in May 2020. I think that might have been the same day.
It is the same day, James.
Oh. We've had just under, sneaking up on the quarter of a million pieces of telemetry through the system. So that's 250,000 disruptions over the time period now. Again, down the bottom of the graph there, got a bit of a breakdown by indicator type and category. Not surprisingly, remote scanning or exploitation makes up a significant portion, but phishing and malware activity are a non-zero amount of that activity. And what time of day do we see sightings? Well, all the time. This activity is just going on around the clock. What day of the week? Well, this was kind of interesting, actually. We sort of thought this one this came out slightly differently from what we expected. You can see that there is a slight offset. So the Saturday levels seem to be a bit higher than we kind of initially thought. This could be because there's a lag potentially in the activity occurring, or it could be because the actors that are doing this are not in the New Zealand time zone. There are a couple of different reasons for why that might be. And we've got another slide a little bit later on which has a bit more insight into this as well.
Cheers. I'll take the talking stick. So when we were having a look at the data set and trying to pull some interesting data out of it to present, one of the questions we had is, do the events we see target a single organisation, or do they target multiple organisations? Is this an everything, or are these actors like going after one organisation? So that was a question. And so he started spelunking through this data and trying to find some answers. Here's a graph, and what this shows is the total number of, so each dot is an event, all right? So, hits on an indicator. And along the x-axis there, we have the total number of sightings for that event. So the one over here, just above 12,000 disruptions for that event. And up the y-axis is the number of organizations that saw that event. So there's a couple of regions here which tend to be interesting. The first one is up here, right? So this is relatively large, number of disruptions, but also, relatively large amount of organizations that saw exactly that same activity. So this is the kind of, large-scale spray and pray kind of thing. But it happens, but it doesn't happen all that often, okay? So these large kind of events aren't what we see regularly. The second region is over here, and this is kind of what we see a lot more of. Now, the purple here is remote scanning or exploitation. Sorry for the ridiculously small 2-point font on that slide. I guess you can download and zoom in later. But all of the remote scanning happens up in here. So actors that are looking for particular vulnerabilities, but it's not across everyone. But it's it's certainly not across one or two places. And as you look down here, the amount of purple gets lower and lower. All of the malware activity and phishing is clustered around very specific to individual organizations. So when we see those malware activity hits or the phishing, they are way more targeted. So people aren't going out and just going after everyone. They kind of know where they want those targeted. Another question we had was, how quickly do we see malicious activity after the IOCs are published? So indicators get produced by the feed providers, we ingest them. How quick do we see activity after that? Another graph. Hopefully you can see the log scale down the bottom. This is time on the bottom here. Okay, so from 1 minute, 1 hour, 1 day, 1 month, etc. So, and this is how many disruptions happened within this amount of time of the indicator. So, us seeing our first piece of disruption 1 minute after would be right down here, 1 hour, etc. And we see, the bump here is at about 18 hours. But there's still a significant amount within the first hour. So if those indicators are coming in at 3 in the morning, like we saw on the graph, like they come in all the time, then we are seeing disruptions within the first hour, but certainly within the first 18 hours of those indicators being live. The land speed record was actually 77 seconds. So feed provider produced the IOC, it was in the feed, we ingested it, it was available for tasking, we tasked it into the client, and 30 seconds later, after it got tasked in, then we started seeing blocks based on it. They took another 47 seconds to get us the notification back, so 77 seconds from the indicator being available to us getting the first block back. So yeah, this really goes to that if you're not having this in an automated way and this isn't happening for you all the time, real time, then you are increasing that risk and not mitigating those risks. Mitigating being a word that apparently I need to say. The other end of this is how long do indicators remain relevant for? So clearly we know what the ramp up is now. What's the other side of this graph? And here, same sort of axes. And how long do we see sightings for any particular indicator? And there's a massive cliff here at about 5 days. Anyone hazard a guess as to why that might be? That for most of the time we just don't see any hits more than 5 days after an indicator comes in. Could be. Tim said it gets patched. Yep. Anyone else want to hazard a guess? It's a Saturday. Yeah, exactly. Something goes weird on a Saturday. Yeah, nice one. The indicators have expiry times. Okay, and for IPv4 indicators, most of the time that expiry is 5 days. So the feed providers, when they put the indicators in, it has an expiry on it. IP indicators normally are 5 days. So we're seeing a lot of stuff just stop after that 5 day period. Anyone notice that this little green smudge up here, like above 1 year? So that happens. So the Rip Van Winkle indicator, once upon a time there was an indicator, it was created in August 2020, and we saw nothing at all, until 2.28 years later, we started getting hits on it. So yeah, 833 days later, I'm started getting disruptions on this. And so after just having told you that indicators have expiries and they kind of age out, what the heck's going on here? And the feed providers can put these indicators back in, right? So when they age out, they can decide, oh no, this is actually something that I want to keep going. Put it back in, give it another 5 days, another 5 days, another 5 days. So they can keep expiring and then getting put back in. Or they can just keep on getting refreshed. So before the indicator expires, they can say, no, just keep it going. And this was actually the case with this indicator, is that the feed provider decided that this was something that just needed to be kept in there for over 2.5 years. And eventually it paid off. Here are some more interesting examples of these indicators that just keep on getting put in and can keep on coming back. So there's 3 indicators here. I'll come over here for the people over here to see the dot. So these are 3 different indicators. One of them's a remote scanning indicator, another one's a malware activity indicator, and this one's a phishing indicator. They've both been put into our system in the feed 28 times each over, from 2021 down to, this year. So they just keep coming back in. And the remote scanning one has, paid off twice. We saw it twice in this iteration and about 33 times in this iteration. The malware activity one, it goes in, we still haven't seen any hits. The phishing one, almost every time that gets tasked in, it gets hits on it. So yeah, 3 indicators, 28 times each, but very, very different activity across them all. Over to James.
Cheers. So we thought we'd kind of pull out 2 or 3 specific kind of events that have occurred that you guys might find interesting. And the first one happened around New Year this year. So let's have a look at that. This is a graph of the telemetry from our system from Boxing Day through to 17th of January. And you might look at this graph and go, oh, well, what's interesting here? And I guess most people's sort of eyes are going to be drawn to this big spiky bit over on the right-hand side here. And that probably looks like the bit that most people would think, that's interesting, big spike, I wonder what's going on there. And that is interesting. But if you colorize it by the customers, then all of a sudden the purple line along the bottom becomes more interesting because the graph, the spiky bit on the right-hand side, we see that's actually across a number of organisations, but this continuous purple activity along the bottom is not usual. So if we dig into that a little bit, and we overlay the type of activity that is, we can see that there's a fairly consistent line against the malware activity category, and that is never a good sign. That is quite interesting. And then if we drill into that particular customer's activity over that time period, we see this. Now, if I was to hypothesize about what this might be, I think I would be fairly safe in saying that that customer had some malware on their network that was beaconing out to a C2 node on a regular basis, and that they should probably be running some IR.
Happy New Year.
So that's the kind of thing that we see where initially you're looking at the graphs and you might kind of focus on one particular area, but when you pull a different lens onto it, something else springs out. Here's another example. Again, your eye is probably drawn to the spike in the orange there. And again, that is interesting. Wonder what's going on there. But if we overlay the category types, again, we see a fairly concentrated but very small section of malware activity occurring. That's always interesting. So if we drill in on that, oh yeah, there it is again. There's another example of a single org seeing a really consistent set of disruptions on an indicator that's associated with malware activity. So that is probably the thing that we want to go and investigate. Your turn again, Dean.
Cool, thank you. Yeah, so we wanted to look a little bit more about, because we have some context about the indicators in terms of those categories, but we don't have much more context than that from the feed providers. But we wanted to see what we could tell about the actor's capability based on what we were seeing. So let's have a little bit of a look at that. Here's some graphs which were taken from the everyone's having a bad day slide that we did earlier, right? So let's dig into that a little bit more. The top one is showing the organization's view. So, every different color is a different organization. Organization A, B, C in the pink, and D down here. Clearly having some attention from this. And, a good spread across the number of indicators as well. So this isn't just one IP address causing this. This is a number of IP addresses causing this attention across a number of organizations. So let's go and have a look a little bit more at what was going on here. So in terms of sources and indicators, here was the kind of breakdown. So things to note here, it's relatively uniform how many packets we're seeing from each of those sources. So this isn't just, a lot of different actors deciding to all be active on one particular day. This is far too regular for that. The other thing we notice is that there's a relatively good spread across the address range, right? So like these two here were in this /16, these two were in that /16, another two, another two, another two, 3 here, and so on and so on and so on. And so whoever is causing this event has infrastructure deployed across quite a large range of stuff. This isn't just go and buy one VPS and hope for the best. This is a relatively large deployment. in terms of the other side of this, so what we saw from those, organisations A, B, and C, they, that was the sort of number of disruptions that they were seeing, and I thought, okay, well that's cool. And then some of the numbers started to, really stand out to me, and I'm like, well, my power of two kind of spidey sense was going off. And some of these look remarkably like the number of IP addresses you would hit if you had a /19 and you were scanning a customer's entire range. Now we kind of know from doing some other background stuff that this was someone looking for a particular Fortinet vulnerability that had just come out, right? So they're looking for places that are susceptible to this and going after it, and they're just looking across people's entire address space for that particular vulnerability. This is a lot harder to work out what's going on than Shane's really good. I'll put up some news articles. That's awesome. I wish I could do that for these, but sometimes it's a bit of guesswork goes on. But yeah, that was kind of interesting. So the takeaways here is, quite a large amount of infrastructure being used to launch this, and pretty much looking for one particular thing across any IP address within the organisations that they could. This is another event here. So again, there's something going on here with organisation B with a couple of indicators. But the one I want to drill into a little bit more is down here with organisation A. And if we zoom in, we see here that within the same 24, we're getting some hits from .3, .5, .7, .9, .11. Thought I was onto a trend. .12 shows up. Stink. But again, seeing similar sorts of numbers from each of those sources, so someone doesn't just have one botnet thing on one IP. Clearly they've got it across a range within that 24. Also interesting here was they were giving a lot of attention to organisation A, and then they sent 2 packets to organisation B. It's like, oh, weird. Okay, why only 2? Don't know. Some other examples, I won't go into this one too much. Everything seems to come only from one IP address. Organisations A, B, and C getting some attention here, and then a little bit later, they drop out organisation B. So this has got me thinking: is this just a spray across the entire New Zealand address space? But we do see this kind of, all of a sudden, one of the organisations will just stop seeing it, and then it might come back for them, a little bit later. But things do seem a little bit organisation by organisation rather than just spraying across everywhere. Here again, looking a little bit at the different indicators here. IP address Y in the blue, quite a bit of activity. Organisation X.144 is in the dark blue, and then all of a sudden that dark blue stops, and a different IP address but within the same range starts up that task again. So, all right, might be another home DSL router within that same ISP, but seems a bit coincidental. The last one I've got is a little bit more time relevant. So from early March here, and this is malware activity on one particular indicator, and we just started seeing this popping up across customer after customer after customer. This same indicator. It started off with organisation A, and then B turned up, and then C, but it would keep coming back. So C here for a little while, and then pops up a day later, and then back to B. and just more and more orgs. And we did a bit of digging into this, and then the news articles, and I really regret now I didn't take some screenshots of news articles. Emotet's back, right? So that looks like kind of what this is more and more people are seeing that coming back. And for some more stranger things, I'll hand back to James.
Cheers. Cheers, Dean. So got a couple of slides here at the end of some interesting things that we discovered in our data spelunking. So one of the things that I kind of was curious about was whether or not we had ever seen an indicator that had been disrupted both inbound and outbound by the same organisation. And that's fairly unusual. Normally you would see an indicator just in one direction or the other. And we have. It has occurred on numerous occasions, as it turns out. But the interesting thing about this was that the inbound and outbound traffic was almost always a different protocol on a different port. So in this case, we had a couple of outbound UDP requests in the red at the start of the graph there. And then a little while later, some inbound HTTP from the same indicator. And then here's another example, just a single outbound UDP event, and then a whole bunch of inbound HTTP. And you might be thinking, well, maybe that initial UDP connection, tickled the infrastructure, and now they're getting a bit of inbound detention because of that, except these are all disruptions. So that outbound UDP never got there. So why did they get the inbound detention? I don't know. It's kind of curious. But this has actually happened a number of times. Here's another example, just a single outbound UDP one at the start, quite a bit of attention inbound in a very short space of time, and then 4 months later, they came back for another couple of goes. And then another one, again, similar sort of thing, with some interesting clustering around the inbound requests. So we've got a little bit more information, a little bit more digging to do here, and a little bit more analysis to see if we can figure out what some of this activity is. Obviously, we're somewhat limited in what we can infer, given that we don't have full packet captures and things like that. But you can actually discern quite a bit from the behaviour of the actors based on a limited amount of data. So where to next?
Yeah, cool. So if anyone's got any ideas about what that stuff is, let us know, whether it's in questions time or at lunch, because we don't know. Again, those are all disruptions. Those packets never arrived at their destination because they got stopped. So yeah, why the outbound triggering before all the inbound? Weird. Where to next? Yeah, there's more interesting stuff in this data. Like we're looking at doing some more trending stuff. Some of the time series stuff that Shane was talking about but I'm thinking about some of that stuff as well. Rich was talking about Gribby, and I'm totally going to adopt that pronunciation of it now. But looking at some of the tasking into routing infrastructures using either that or BGP flow spec, and being able to take those indicators in the most timely way possible. And we see the 77-second example, right? And being able to task those in to routing infrastructures, not just firewalls, and going from there. So yeah, that's kind of where we're going. If anyone's got any interesting things they would like to know about what we see in the data set, come and have a chat, and we'll see if we can pull it out. Yeah. Cool. Questions? We're done. No, all good? Sweet.
So now we've got a couple of update sessions before lunch. So first of all, we've got Rachel and Norman from NCSC.
Can everybody hear me? Oh, yeah. Kia ora koutou. Kia tātou e hui hui nei mō tēnei kaupapa. Kia tau te rangi Māori. Ko Norman toku ingoa e noho ana au ki Tamaki Makaurau. Greetings everyone. I see a lot of familiar faces around. For those who don't know me, my name is Norman Vai. And I am a Senior Technical Security Assessor within the NCSC, within the Texas team. Tēnā koutou, tēnā koutou, tēnā tātou katoa.
Tēnā koe, Norm. Ko Rachel tōkou ingoa, no Tamaki Makaurau, aho. For those that I haven't had the pleasure of meeting, my name is Rachel. I'm a consultant within the NCSC TIXA team. As we know, there's been some devastating weather events throughout New Zealand. And we'd like to thank you, our NZNOG community, for assisting those Kiwis and those organisations that have been impacted and continue to be impacted by Cyclone Gabrielle. Before we kick into the presentation today, just to understand my audience, hands up who's seen us present at NZNOG before our TIXA roadshow. Great, look, we have a mix of people within the audience today here, Norm.
Yes, we do.
So look, first and foremost, you may note that there's two of us on the stage here today. So I'm going to talk from a consultant perspective, and Norm is going to assist from the assessor side of things. And we're going to take you on a TIXA journey, and it's only going to take 15 minutes or less. The agenda for today, I'll introduce you to a few of the other folk from our TIXA team that are here. We'll discuss what is TIXA and why it's important to you to notify us. And then we'll take you through the notification process from the assessor lens. And finally, we'll conclude our presentation with some updates from our NCSC Cyber Threat Report. So, joining me and our TIXA team here today, we have Joe. We also have Elizabeth, Steve, and William. So what is TIXA and why do you need to notify? At a high level, there's 4 parts to the Act. Part 1 looks after the principles and definitions of the Act. Part 2 relates to the duties of operators of public telecommunications networks to be intercept capable. Now, NZ Police look after that, part 2 of the Act. And part 3, network security. So that is what we're going to focus our presentation on today. And part 4 is the enforcement and the running of the Act. The key things to note is part 2 and part 3 apply to you all. When we're out engaging with network operators, we're often asked, what do we need to notify? And that is a really good question, and we're here to answer that question for you. Section 47 of the TIXA is areas of specified security interests, or the ASIs, as Norm likes to refer to them. So any changes that you make to your NOC functions, any changes that you make to privileged administrative users, or your LI architecture, points of interconnect, and changes to high traffic areas are all notifiable. Norm, please feel free to take us through some of the ASIs.
Tēnā koe, Rach. So when we receive a notification, so the first thing that we actually check against is actually against these ASIs. If it falls within there, then that's how we determine whether it's notifiable or not. If it's not notifiable, we'll simply email you back say it's not notifiable, and then give reasons as to why it's not. If it is notifiable, we will then start our assessment. Now, as an assessor, when we're performing our assessment, there are a number of principles that we adhere to, frame of mind, and I'm just going to talk about a few of those, just to give you an insight. So the first thing is, right from the outset, we presume that you, the network operator, is competent in the running and operating of your network. You understand the cost that goes into just maintaining and sustaining your network, the underlying technology. We don't tell you how to design your networks. You're the experts. Nor do we tell you how to manage them. We presume that you're competent because it's inferred, in fact, that you're actually in business. Now, one of the things that we do check is we check that there is no intelligence on the equipment or systems that you are looking or seeking to deploy into your networks. We also check on third parties in which you may be possibly considering to do business with. And that could be in the area of design, installation, or support. Now, we will tell you any risks that we identify. I will talk more about our assessment process in the next few slides.
A couple of other things to note is that you can also self-identify a network security risk. So if you became aware of a change or a cause of action, you should notify us. So for example, any emergency changes that you did during Cyclone Gabrielle, you should notify us. We make decisions on network security risks. We make them independently. All your notifications are in commercial in confidence. All our notifications are on a case-by-case basis. And we work cooperatively and collaboratively with you, our network operators. Other things that we take into consideration in our assessments are Section 50 sectors and services, which are listed on the screen here today, and any other matter the Director General considers relevant.
So Section 50 is a key consideration for us. And often we use this as a good indicator for us from an impact perspective when we're performing our assessments. If ever, now I don't know how some of you have managed to give us a notification where there is no Section 50 services in there, it is highly likely that we will find no risk. Now there's a strong correlation between the size and scale of your network and the number of Section 50 services that consume your services. Now, we acknowledge and also recognize that each operator has different standards, has different security standards. And also, they have a different risk appetite. And again, that's proportion to your size and your scale of your network. There are circumstances where certain operators may be the only provider for some of these services. That's key information for us to know.
The other question we're often asked is, what is the process and how long will my notification take? And once again, this is a really good question. So a notification form is on our website. You download the form, you fill it in and you send it to us. Within 3 days, we'll come back to you and let you know that we've received your TICSA notification. Now, we have self-imposed SLAs, or magic working days. As a government agency, our Hours are Monday to Friday, 9 till 5. So you've sent your notification in, we've received it, we'll come back to you with a regulatory number, and then we'll start our assessment. Now, if during that time we have some questions, and I mentioned previously that it's a collaboration approach, if we have some questions, we also have what we call in government is my magic clock. So we stop the clock, we fire off an email to you, you'll come back with some further information, some diagrams or anything that our assessors may require to complete their assessment. We've got all that information in hand, and then we start our magic clock again. So within 20 our SLA days, we should come back to you with an answer on that assessment. However, if we find a risk, it will take time. It moves into that mitigation phase. There's no SLAs. We assessed 160 notifications last year, and as mentioned, all our assessments are commercial in confidence.
So one thing that adds to the timeline of you submitting a notification and getting a result or a determination from us is often the information gathering when we come to you to get more information so that we can better understand your notification. One principle that we always follow is proportionality, and that is we ensure that the effort that goes in to ascertain that information is proportioned to the perceived risk or national risk that we look at. We also strive to ensure that the notification process does not hinder your day-to-day operations or your delivery timelines. Please use your existing documentation to support your notification when it comes in. Between you and I, between us, we can actually get that information earlier so we can turn around a notification a lot faster. Now, super important to note is that our assessment is based on the information that's available to us at that point in time.
Excellent. So what we suggest is this. Engage with us early during your procurement, your RFP, during those processes, engage with us. As previously mentioned, if we find a network security risk, it will take time. Your timelines will be stretched. If there are any key takeaways for your organisations on mitigations, it's the info on this slide. And finally, some updates from our NCSC 2021-22 Cyber Threat Report, which is available. We've got some copies down the front here. It's also downloadable on our website. So some stats and figures there. I won't go into the detail of them because you can all have a look at the report or download it yourselves. But the key things that I do want to touch on is that the numbers on the slide represent that despite all of our defensive efforts to assist our organisations with uplifting their cybersecurity posture, bad stuff happens, and it happens on the internet.
Yes, it does. Some of you might think you're too small to be a target. Just know this, that your network can be a conduit that others see to use against your other operators, because you do consume services from each other.
So we have some free space. Is there any questions for us? Looks like there's no, oh yes, question down the back there.
I hope this is a simple one. Is there a threshold for number of subscribers? Is it 1,000 or 10,000 or fewer or more before you have to be TICSA compliant?
Sorry, I could barely hear the question. Sorry, what was that again?
Is there a threshold for subscriber numbers before you are subject to the regulation?
Right. Okay, so under the TICSA, there's a 2,000 number. That's for allies specific. For Section 3, we have come around a figure which is still, it's still contingent on the situation when we're looking at a notification. For example, if it's quite niche services that are quite critical, dams and certain things, you can imagine the numbers are not going to be, we're not going to say it's going to be 10,000 subscribers and so forth. The general number that we had sort of discussed was around about 10,000. Steve, please correct me if I'm right.
So Section 3 of the Act applies to all network operators regardless of size.
Correct.
But what's the data point there is that it's 10,000 customers' information at rest.
Correct.
But that's a different part. But Section 3 applies to all network operators regardless of size. Everybody should be notified of changes to their network.
So the result of that is, regardless of size, for Section 3, you need to notify. In short.
Any further questions? So look, just to wrap things up, there's this thing called TIPSA. You need to notify. We are here to help. We work cooperatively and collaboratively with you. The team are here, so any further questions, feel free to hit us up after lunch. You can email us, information on our website. Thank you for your time today.
Yep. Thank you. I hope you enjoy the rest of the conference. Kua mutu ia mā ua kōrero mō tēnei rā. Nō reira, tēnā koutou. Tēnā koutou, kia ora koutou. Thank you.
Okay, so one more before lunch. So Shane is going to bookend this session with a different presentation, a more traditional update of his.
Hi, it's me again. I'm Shane, and today I work for myself again, but it's complicated, and that's what this talk is about. So yeah, it's going to be a little bit less technical than usual because we've gone through a few changes in the last few months, and the whole point of this talk is to bring you up to date with that. So the first thing, those of you who are not aware, and I've not managed to inform today or at this conference, the WAND Network Research Group has sadly passed from existence last year. All of us have gone our own separate ways, and we're doing okay. It's okay. We've landed on our feet. But from an OpenLI perspective, obviously, there were a couple of things that we had to resolve. Firstly, that all of the servers and the networking equipment that I was using for development and testing have gone away, which is a bit of a bummer. But also, I was left without a line manager, which was also not ideal. Fortunately, Richard and I had been working with the people at Waikato Link for quite a while up to this point. They're the commercialization office at the university. And we've been working with them to, try to find ways to make OpenLI something that could stand on its own financially. So basically, it was a very smooth transition from WAND to, Waikato Link being the stewards of the project, which was all well and good up until the start of this year. Waikato Link informed Richard and I that they had decided to end their involvement with the OpenLI project, and so therefore we would have to find a new home. They would emphasise, of course, that all existing contractual arrangements with clients would still be met, so anyone who had paid the university for support would continue to receive support. Anyone who had granted us money for further development would still happen, but ultimately we needed to find a new home, and the university would not be taking on any new support contracts or renewing any ones that expired. And so Rich and I are now no longer at the university. Kinda. All right, so Waikato is now subcontracting me to meet their support obligations for now. So if you're an existing client, nothing has really changed for you in practice. If you need me to do stuff for you, then you can reach out to me and I will do it because I'm getting paid for it. In the immediate aftermath, Richard and I sat down and agreed that OpenLI is still useful. We still want to try and make this thing work, and so we were going to keep going. It was really important to us, of course, that OpenLI remain open source because it's in the name, but also, that was the sort of community-oriented organisation that we'd created thus far. So we want to keep it open source. We want to keep it freely available. But at the same time, we still kind of need to pay some bills. So I am very excited to announce that our friends at Searchlight have agreed to take us on and give us a new home. So this is going to be very exciting. We've been working with the Searchlight guys quite a lot over the past couple of years as well, so it was really a natural fit for us to just try and bring it all together and combine their operational expertise with me writing code. So in the short term, it's basically just going to be business as usual. So the same support contracts that were being offered by the university will now be offered by Searchlight. So you can buy access to me if you want it. Longer term, we're still sort of got to sit down and work out what ideas we want to pursue, but the idea would be to develop some more sophisticated offerings, something that might appeal a lot more to international clients, bigger clients, people who just want to pay lots of money to have LI sorted for them. And so we'll have a brainstorming session fairly shortly and work out what that is. And hopefully that will help sort of subsidize the whole open side of OpenLI. Because there may be some concerns about the fact that we are joining up with a slightly more commercial entity than a university, I want to reassure you that we are taking some steps as well to try and sort of protect the OpenLI brand and make sure that it's sort of its own separate entity. Since we're dealing with a lot of paperwork as it is, Rich and I haven't quite had much time to work on this yet. So we haven't really worked out what form that's going to take, whether it's some sort of trust or not-for-profit company or something else. But the idea is that we would act as custodians and maybe try to bring in also some representatives from the user community to provide a bit more of an independent voice. And that entity would end up taking ownership of the copyright to the source code, for instance, the OpenLI trademark, branding, logos, any media, website, that sort of thing. Okay, let's talk about some technical stuff because that's much more fun. So there's been a couple of releases since I spoke to you last time. So the latest 1.0.15. It's mostly just some bug fixes and updates to make sure that we support the latest versions of things, especially DPDK, which likes to break stuff with every major release. We had a user request that I was very happy to implement. So SIP target usernames on your intercepts will now support an asterisk as a leading wildcard character because they were having issues where they would see incoming identities that had just about every combination of area code and plus and not plus, international dialing codes or whatever. So it was a hell of a lot easier to just stick a star in front of the base number and have everything work rather than trying to guess every combination. So the reason I've only done a couple of little releases is because behind the scenes I've been working quite hard on this new 1.1.0 release. It's going to add full ETSI compliant email interception. Not that anyone here needs it right now, but just to let certain people know that if they decide that they want to start intercepting emails, then we can do it. And a lot of work on the mediator, making it more robust in terms of buffering so things don't go missing if you happen to restart the mediator, and a lot more parallelism as well because it was becoming a bit of a bottleneck. So now we treat every agency that we're sending intercept records to as a separate thread, and every collector that talks to the mediator is now treated as a separate thread, so they don't all compete with one another for the same CPU cycles. So this is going to be released very, very soon. Oops. And the other thing that we've added that is going to be released very, very soon, but I couldn't quite get it done in time, is a simple web UI for the provisioning side of things. And this isn't written by me. This is Andrew Simmons in his final few weeks with the WAND group, wrote this one for us, so much credit to him. So it's the front end for the entire provisioning API that we have. It's going to be a separate package, again, open source, freely available, and you can use it as a starting point if you want to develop a more sophisticated UI or something with your own branding on it or whatever you want to do. So again, very close to being released, just a little bit more spit and polish to go on that one. And in particular, I've got to figure out how to like package a React Bootstrap thing so that it installs nicely. So that's a quick screenshot of what the UI looks like. You probably can't see that much of it from there, but it looks like a UI. And there's another one. Oh, it's got some colors on this one. Right, so the other things that we're going to be doing in the coming year, the university won a grant from ISIF Asia for us to assist with helping out our friends in the Pacific with their LI needs or their potential upcoming LI needs since the laws have been changing over there. So there's a few tasks on our possible to-do list. The first one, well, we've almost knocked that one off already, improving the usability by providing a UI. One of the big things that we're going to be aiming to do, and it's probably going to take up a lot of Richard's time, is preparing to run training events over there to help upskill the operators, teach them about not just OpenLI itself, but LI concepts in general. A lot of that will be based on the tutorial work that I did a couple of years back with the previous ISIF grant. And the other fun thing that we're starting to think about looking into is trying to develop sort of an open LEA. So doing the other side of the equation, the receiving side, and maybe use that, something that agencies in countries that perhaps are not as well funded as other agencies could use instead of forking out a massive amount of money for a commercial solution. So, kind of getting into both sides of the game. So to quickly sum up before we go to lunch, so OpenLI has left the University of Waikato, but we will be meeting all contractual obligations. However, we still live on. Software is still going to be open source. Nothing's going to change in that regard. And eventually there will be some sort of entity that takes ownership of the OpenLI. I guess you call it IP, but it's not really that. So our new home is going to be Searchlight. They're the people who have provided your coffee cups. You'll see lawful interception written on them. That's kind of, I guess, that was the sneaky foreshadowing of the content of this talk. So we're going to be offering the same services that we've been offering up until now. So, you'll just be dealing with a different organisation. Right? And then, we're going to be working towards adding more exciting value-added services that may not necessarily be for you, but hopefully will appeal to particularly overseas customers, potential customers. And that's it. Thank you. If there are any questions, feel free. Otherwise, find me at lunch.
Okay, as Shane mentioned, that's now lunchtime, so we're just about on time, so we'll be back here at 1:30 for the final session. We've still got space for lightning talks if anybody wants to do a lightning talk.
don't need it.
Cool.
Give me 2 seconds.
There's a list there, you just need a random number to it.
What is it between?
191, but check the numbers, because not all the numbers are there. And don't call out a couple of wives.
Yes, well, so after I picked the first one, I printed out All right, let's kick back into it. I just asked this thing for a random number between 1 and 190 and it gave me 0. So let me do this again. Right, 122, Roy Hall. Is there Roy Hall here? You clicked it for him. Are we doing that? Or are we rolling again? Roll again. 94. 94. Cat Dearlove from Extreme. Roll again. Paya Maru. Roll again. Jimmy Chen, 2 degrees. I think 2 degrees. Hey. Thank you, Go Wi-Fi. Thank you. New core switch. Okay, so this is the last session. After this, we've got the break, and then everyone can disappear. So first up, we've got Conrad Bullock from Rooster talking about EVPN scaling.
Hey guys, thanks everyone. I'm Conrad Bullock. I'm a systems enginear with Arista Networks. I'm based in Wellington. But I am also that numpty who came a cropper on the luge last night. So I blame whoever sponsored the dinner at the Skyline. But today I'm actually going to talk a nice deep technical session for straight after lunch on the last day. I'm going to talk about BGP EVPN gateway and how it can be used for hierarchical scaling and data center interconnect. In the data center in particular, EVPN with VXLAN encapsulation has sort of become the standards-based approach for delivering VPN services across a shared leaf-spine architecture. The maturity of EVPN and the benefits it provides has meant it's grown within the data center, but also across data centers for service continuity. Now, this growth is great, but it has raised the number of scaling and data center interconnect challenges, when we're still trying to provide that seamless layer 2 and layer 3 service across EVPN domains. So in this session, we're going to look at the work done by the IETF BESS group. BESS is BGP-enabled services. That working group, and how we can use it to deliver a standards-based approach for scaling EVPN domains and data center interconnect across MPLS and IP backbones. So, starting off with some questions, why do we use EVPN? Well, ultimately, it's about simplification. Rather than running multiple complex state-intensive control plane protocols, which have been developed in isolation, we have the ability to run a single BGP EVPN control plane to support the different service types. And this is the case even if we're using different data planes. So with BGP EVPN, we get to keep things simple and consistent, balanced approach to resiliency, and simplified automation and performance at scale. If we consider the basic idea of an EVPN gateway, an obvious use case is provide a mechanism to connect EVPN to another protocol for interoperability, for migration. For example, to help migrate from IPVPN to VPLS or VPLS to EVPN. And so I would be curious to have a chat with any of you afterwards about the challenges you've seen with doing that migration from those legacy control planes to new ones, going from a brownfield environment to EVPN, and the challenges of trying to get that functionality out of one box, or whether you prefer to keep that separate. But more on that a little later. But specifically, I want to look at the role of EVPN gateways for building multi-EVPN domains. So in terms of EVPN gateway, I'm looking at two problems here. The first solution, first problem we're looking at is the idea of building an EVPN data center interconnect, where we've got multiple EVPN domains geographically dispersed, and they're connected by some sort of MPLS backbone. And there's a requirement to provide layer 3 or layer 2 connectivity across that backbone between those domains. The second challenge we're looking at is the question of EVPN scaling. We're seeing more and more customers who are deploying data center fabrics, getting larger and larger, potentially 100, 150 leafs in an EVPN domain. At the same time, they want to deploy any workload anywhere model. So they're stretching VLANs across every single leaf, and potentially providing layer 3 connectivity across any leaf as well. So that has implications in terms of flood lists, and if you're stretching your layer 2 VLANs everywhere, there's state churn, MAC addresses, IMETs, MAC IPs, routes, and if there's any failure or event, then there's potentially a large amount of state churn that spans across the domain. So we're going to look at how we can use that any workload anywhere model, but in a way that we introduce a hierarchy so that we can scale better, reduce the flood domains, reduce the state churn, and still retain the ability to do our layer 2 and layer 3 stretch. So we talk about data center interconnect and interconnecting EVPN. Of course, we've always been able to do that. Traditionally, you'd have a border leaf inside your local EVPN domain, and then if you wanted to stretch across your MPLS backbone, you'd do some sort of option A handoff, or a VRF Lite handoff into a PE node. The PE node would then be running IPVPN or EVPN MPLS, learn those routes from the local EVPN, and then re-advertise them. And that's something we can continue to do, of course. You can do a similar type of option A VLAN handoff to interconnect to another EVPN domain, may just be in the same site. But the idea with the EVPN gateway is we're giving the capability of collapsing that two-box solution into a single box, the EVPN gateway node, as shown here. So this EVPN gateway can give us connectivity to the local EVPN domain, provide a hierarchical model that allows us to control the scope of routes as they go between these domains and what you advertise to the neighbours, but also provide MPLS functionality where we can do an address level translation from EVPN to IPVPN or VPLS, or an encapsulation change to go from EVPN VXLAN to EVPN MPLS, for example. If we do that in a single box, then obviously less hardware, but also fewer boxes to touch in terms of actually running those services. So we're talking about a bunch of different solutions, different data planes, different control planes, and there's a number of different standards out there that deal with these different models, layer 2 and layer 3. First one here is, we've got the layer 2 EVPN RFC. It's very mature, supported across the industry, across multiple vendors, and that describes how gateways work. For the layer 3 model, we talk about the translation between EVPN and IPVPN, so the layer 3 model on the gateway, that's also a fairly mature standard. When we start looking at stretching layer 2 across different domains over an MPLS or IP transport, there are multiple drafts in terms of looking to solve the similar problem. They're not all equivalent one-to-one, so there's the DCI EVPN RFC 9014, which is very far-reaching. It covers multiple encapsulations, so we've got our VXLAN MPLS, provider backbone bridging, and it's not just EVPN, it also looks to solve when you've got VPLS in your backbone. The Sharma draft is slightly more restrictive. It just focuses on one use case, which is EVPN VXLAN to EVPN VXLAN. There's a draft that covers inter-domain multicast forwarding. And the final one here, the DPath draft, is, we can prevent loops in a multi-domain environment. Effectively, it adds a domain identifier to routes as they go between domains. So, lots of standards, and a little later on I'll talk about the testing that is going on to ensure that these work in a multi-vendor environment. But I'm just going to go into a little bit more depth into these particular combinations. There's a few combinations of control plane and data plane that can be deployed, but I'm just going to call out some common scenarios. The first scenario here, we're interconnecting two separate EVPN domains via an MPLS IPVPN interconnect. The gateway itself runs as a PE. It takes local Type 5 routes from our EVPN and then re-advertises them into an IPVPN MPLS route. The second one, it's a slightly different model. It's the same use case. We've got two EVPN domains interconnected via MPLS, but instead of IPVPN, I can run EVPN MPLS between the two gateways, and now I can do layer 2 as well as my layer 3 stretch. And finally, the scenario here is where we've got IP connectivity rather than MPLS between our domains. So we can use that, the EVPN gateway, to control, provide a level of hierarchy and control what's going between the domains. And we'll talk about how that works with flood lists and state churn. And that's a common scenario for scaling within the data center. So just diving into a bit more detail on that first one, really it's pretty straightforward. We've got the layer 3 interconnect between EVPN domains with IPVPN in the middle. It's a mature, widely implemented standard, and effectively the gateway is doing the translation from a Type 5 route in EVPN into an IPVPN MPLS route. Now, if we look at the EVPN to EVPN gateways, which is really the heart of RFC 9014, we can see how it can be used to provide a solution to both data center interconnect and scaling. For data center interconnect, we can support either MPLS or VXLAN encapsulation. And for scaling out in a data center, we'd generally be using an IP interconnect, IP backbone. In both cases, we're doing EVPN end-to-end with the gateway providing the hierarchy. And there's a little summary up here of how it works for layer 2 and layer 3, but we're going to go and look at that in the next few slides. So we may have, in this case, we've got an IP connection between EVPN VXLAN domains. We might be doing this for interconnect, it might be for fault containment, or it might be for scale. And these can be deployed within or between data centers. And we've got this requirement here to provide our layer 2 and 3 VPN services across the domains. So we have a gateway node deployed in each of our local domains. And these gateway nodes are in the local domain, but they're also providing connectivity to the other gateways in a remote domain. And this local versus remote is where we get our hierarchy, and the gateway becomes the control point as to what passes, in terms of advertisements from one domain to another. And specifically, if I dig into layer 3, effectively what happens is that the gateway nodes are participating in EVPN and the VXLAN forwarding plane. They receive Type 5 routes on EVPN, and then they re-advertise them across the interconnect, but they rewrite their next hop with themselves. Now that hierarchy means that the nodes in this remote domain now no longer need to have reachability information for nodes over here. So our underlay is much simpler in terms of route tables and so on. And from a forwarding plane perspective, just really more for reference, the gateway is decapsulating VXLAN in this domain and then re-encapsulating across the interconnect, and then this gateway is doing the same. From a layer 2 perspective, it's very similar. Similar concept. We've got the gateway nodes participating in EVPN control plane and a VXLAN forwarding plane. The difference here, though, with layer 2, we have these type 1, type 3, type 4 routes, and they are constrained to remain only within the local domain. So these are things around Ethernet segments and so on that we don't need to propagate further. And that's where a lot of that state churn comes from. By preventing it from passing into the rest of the environment, we are improving scalability and performance there. Type 2 routes, not shown here, which are the MAC IP routes, they are passed through, and again, the gateway is rewritten, so we know that the next hop is changed to the gateway. And forwarding, it's just the same, except that rather than routing and VRFs, we've got bridge domains and bridging. Now, what this does also make a difference in layer 2 is with flooding. If you imagine if we had a single domain with all of these endpoints providing access to a layer 2 stretch, then everyone needs to know about all of the other nodes that deal with flooding for broadcast, unknown unicast, and multicast traffic. By constraining those components to the local domains, we effectively build a flood list that's just for this local domain. It knows how to get to local VTEPs and the gateways have a flood list that just shows how to get to the other gateways, and then another one remotely. So down here we can see the flood list is much smaller, so we can scale a lot higher. And really, if we look at using MPLS in the middle instead of IP, so more of a data center interconnect use case, it's pretty much exactly the same principle. Just the difference is that we are decapsulating VXLAN and then re-encapsulating inside MPLS. It's got the same scoping in terms of routes and so on. And this policy point we can also use to apply our summarization, aggregation, all the usual route policy control we might do. And so this looks at the layer 3 forwarding model and the layer 2 forwarding model. They're really just the same, except that we've got MPLS in the middle. It's still EVPN end-to-end. And same with layer 2. So a couple more points I wanted to cover. How do I build resiliency into this gateway function? Here are the sort of the three classic solutions we see in the standards and generally deployed in the industry. On the left-hand side, there's our classic multi-chassis link aggregation type solution, where we've got multiple nodes with a peer link that are sharing a single VTEP. This is the same principle we use inside standard EVPN. The next option there is Anycast IP. So Anycast IP, it scales fantastically well. We can use our ECMP. We don't need to have peer links between the nodes. Just one downside is we can't have endpoints actually attached to those nodes because there's effectively no state exchange there. And the final one that we're seeing is the full active-active gateway. And this is using the same principles that we have in EVPN, the Ethernet segment identifier, but we've got a special one for the interconnect. And this is where the nodes are exchanging state via BGP. It scales up, we don't need peer links, we can have locally attached devices, and we've got a designated forwarder that's dealing with broadcast unknown unicast and multicast traffic. So just finishing off on the EVPN gateway thing, we can look at the topologies that we can use, we can build out with the EVPN gateway. If we're building multi-domains, starting off with, maybe I want to scale up my data centers, maybe I want to have a fabric per hall or a fabric per row. If it's a relatively small number inside my data center, then I can just build a mesh between my gateways, standard full mesh of BGP EVPN sessions. But if I need to scale higher or I'm expecting growth, we can also use other standard techniques. In this example, we've got each fabric is its own EVPN domain, and then we can use spine switches or a super spine to build interconnection between them. And we can use route reflectors or route servers, depending on what flavor of BGP we're using. If I want to scale up across multiple data centers, again, it's the same principles that we know from BGP. We could use an IP or MPLS backbone with route reflectors and standard BGP pairing techniques to scale out this environment. We can have redundant gateways, as we've just discussed, and we're still able to stretch our layer 2 and layer 3 services across this environment. So a little summary on the multi-domain benefits. We've got this reduced network underlay state because we're rewriting the next hop. It means that we only need to learn effectively connectivity for VTEPs or devices in our own domain, plus how to get to the gateway. Reduces the routing table for the underlay significantly. And for the overlay network, the hierarchy allows us to control what routes are passing between different domains. So we can do our summarization, aggregation, and optimization of those routes. Floodless scaling, we talked about. We're reducing the size of the layer 2 flood list. We only need to know about devices in our own domain again. And we do that by restricting the scope of these routes. And that helps us deliver reduced state churn. So if I've got a link up or link down on an Ethernet segment in one domain, it doesn't need to be propagated through the rest of the network. Similarly, if a device moves, Mac moves inside one domain, I don't need to tell the rest of the network because it's still the same gateway they need to get to. So it really helps us with scaling. Now, the final couple of slides, I just wanted to talk about testing. So it's all very well, I've talked about the standards. These standards are deployed by multiple vendors. But how do we know that these things work together? And I wanted to call out the EANTC, or the European Advanced Networking Test Centre. And this is a test centre. It's based in Berlin. They run a global event every year. I mean, they run other sub-events as well, where many different vendors attend and effectively test the latest and greatest in terms of standards, from IETF and elsewhere. It's a very collegial environment. The vendors propose the test cases. Every vendor can choose which ones they want to participate in, and only the successful tests get the results published. And so the EAMTC then produces a report based around these tests. And so here's a kind of a view of the key things from the last 6 years. And we can see that over time it's moved from basic interoperability testing through to gateway and more advanced features as we've gone through time. That's basically because we know the problems on the left are all reasonably well sorted. And so I'd encourage you to seek out these reports. And interestingly enough, the EAMTC for 2023 is happening right at the moment. It's the last day of the event in Berlin today. And I've got a little list here of some of the functions that are the focus for the testing for this year's report. But if you're interested again in following up on this and seeing what the tests show from 2023, the report will be presented and published at the MPLS Congress in Paris next month. So they're all available freely. And you can see the logos up in the top right are the vendors who are participating this year. Okay, so that was a fair old run through a lot of dry technical material, but I am finished. Thank you very much. All good? Cheers. Oops.
Alrighty, next up is Simon from 2 Degrees in person this time, talking about more faults and fixing stuff and, yeah.
All right, so most of you already know me, but my name's Simon, and this week I work for 2 Degrees. You may remember me from my last talk where we talked about flow spec and having an important BCP. And yeah, today is going to be much a similar concept around talking about BCP and why it's so important to actually have a BCP when things go really, really wrong. Before I carry on, though, I do really want to say, while I try and keep this pretty light-hearted, it's not lost on me that people of New Zealand got pretty impacted by Cyclone Gabrielle, and and my heart does go out for the people who actually got impacted and lost their lives. But yeah, I try and keep it light-hearted, but it is, it isn't lost on me. And while I, obviously, 2 Degrees and Vocus are going through a merger, I will refer to the 2 Degrees network as 2 Degrees and Vocus as the Vocus network. That's just to try and deconfuse things, but the reality is we have merged together. We are 2 Degrees. The Vocus brand is going away, but we are running 2 different networks. So, but before I continue, I don't think the lawyers trust me much. So they have said that, whatever you do, make sure you say that these are your own views and not necessarily the views of 2 Degrees. These events that we went through, what I'm going to talk about are mainly, the things that I personally went through and at the company went through. So yeah, if you don't like what I say, come talk to me, don't talk to my employer, but everything will be good. So, here she comes. We knew Cyclone Gabrielle was coming. On that, I think it was the Wednesday before the storm, we all got called into a Lifelines meeting with Auckland Lifeline, and we got briefed by a very excited Met Service meteorologist. And she was literally waving her hands in the air saying, this thing is going to hurt. It is going to cause massive storm surges, it's going to be massive winds, there's going to be a lot of rain, and this is going to be big, and it's going to hurt. So we knew it was coming. We were then able to go and use our field, brief our field force, brief all our partner field forces and get them all prepped up. We knew pretty well where the path was going to be. It was going to come down, hit the top of the North Island, come down the east coast, and then skirt off the side. So we knew it was coming. We could start sending our generators out. We could start briefing the field force, but it really was just a waiting game to see what was going to happen. So it hit Northland pretty hard. It took out a lot of power. In fact, from a Northland point of view, it took out the majority of the power. For us as a telecommunications provider, power problems are relatively easy to fix. You rock up with a generator, you plug your generator in, you move on to the next tower, and you go round and round and round. What we weren't really prepared for is the number of towers it was going to take out, and also the access problems that it caused as well. So getting to some of these high sites and where these towers are located was a massive challenge for us. Trees all over the road, slips everywhere, so we could only actually target a certain amount of cell sites. And generally a cell site, it runs on about 4 to 8 hours of battery life. And the reason why we do that, we don't want to have too many batteries in the field. They're costly, they're not very good for the environment, and majority of the time a localised power cut is 4 to 8 hours, or at least it gives us a chance to roll out a generator in those particular areas. So a lot of the towers went down pretty quickly because we just couldn't get to them. There was a fibre cut as well in the far north, which was a chorus fibre. That was repaired pretty quickly, but for a little time, we obviously had power and a fibre cut to deal with as well. And then as it went down the side, it hit the Bay of Plenty. The Bay of Plenty was actually fairly unscathed, at least from a telecommunications point of view. But all in all, we didn't declare, what we call a MERG or a BCP event because it was fairly under control from a telecommunications point of view, and it was something we can really work on and get sorted. But then it was Tuesday, and Tuesday, whoop, wrong one, there we go. Tuesday was a new day, and we literally woke up and went, what the fuck just happened? Taupo, from a 2 degrees point of view, was offline. All the cell towers, all the fixed 2 degrees was offline. Napier, from a 2 degrees point of view, completely offline. Our Napier Vocus POP used to have several hundred gig, now we're only have 10 gig. And our management network was also down, and Gisborne was offline for both networks. So we're sitting there going, wow, this is a pretty serious event. Shortly after, notified of a national state of emergency, and then also very closely followed by that was a Transpower grid emergency. And shit's really hit the fan when Transpower come up and say we're doing a grid emergency, because they don't do that for shits and giggles, right? They're pretty serious problem when there's a grid emergency. We also then were obviously very concerned about our people. We've got we're a company now of 2,000 employees. We are very concerned about our health and safety of our people. So much to my disgust, we didn't have technology to go around and actually go and text people and say, are you okay, reply to us, etc. So we had to activate the good old 1980s phone tree. And that allowed us to really quickly determine that we actually had people unaccounted for. Which, to be fair, wasn't too surprising because we had a good portion of our network down. And at that point, we basically looked at each other and we said, it's time to activate our BCP. So we call it a MERG. So a MERG stands for, in our language, a Major Incident Response Group. But this is fundamentally built off New Zealand SIMS, which is very similar to what we talked about in the in the Vocus outage. I've got a laser here, I think, haven't I? Yeah, there we go. So what we basically have is, at the top, we have a governance layer. That's our ELT, executive, the C levels, what do you want to call it. They're the ones that basically give guidance, and the bag of gold is required. Underneath this, we have a controller, and that is very similar to, well, it's exactly the same as what the civil defence guys use. And you would have seen that on TV, when they had all the people doing those interviews, they had all their white coats on and stuff. They were generally the controllers. And then underneath that, you have intelligence, operations, PIM, which is your media guys, safety, planning, logistics, and welfare. So in this particular scenario, I actually filled the roles of intelligence and logistics. And then Elisa Petter, who was our NOC manager, she filled the role of controller. We actually did employ a safety person. We've got safety people inside our business, so we did actually have a safety person. We've got a lot of media people. I actually didn't realise how many media people we actually have inside in 2 degrees. turns out quite a lot, and so they filled the role of PIM. And planning we didn't actually use, and then we actually had a person sitting in the welfare seat as well. And yeah, while we don't use the fancy coats, like all the civil defence people do, we just pin them inside a Teams channel, so it's very easy to identify who's who. And then underneath each of the groups, we then had trees. You know, the NOC guys then had the NOC team under operations, and then they had effectively simple groups dealing with, you know, multiple areas. And that's where all our trans ops and field ops and all those guys sort of sat. But it wasn't just us. This ended up being very much a team sport. So we had our incident group going, but we also then spun up what's called TEF. So if you guys aren't aware what TEF is, it's called the Telecommunications Emergency Forum. It's a spin-off of TCF, and it's got all the big players in here, but the main players at the time were Spark, Vodafone, One, Cordia, Chorus, and RCG, and obviously ourselves. And then the TCF group, you know, most people know Claire and Paul Brislin. They actually became the chair of the TEF. And then, yeah, that worked really well, and I'll touch a bit on that in a second. But one important note in there as well is Claire, who was chairing this whole thing. She lived in Piha, so she was heavily affected in her own personal life as well, but still activating, you know, and working with the TEF to make sure it functioned. As well as the TEF, we were obviously in the role I was sitting in as intelligence. I was having to deal with the NEMA guys, having to deal with Hawke's Bay, Bay of Plenty, regional, you know, Northland, Auckland's Lifeline and Gisborne Lifeline. So each one of these had their own lifeline activated too, and we were feeding and being part of that. And that was a really good source of intelligence for us because we were learning about road closures, where the power outages are, you know, where you can't drive, where you can drive, and that's what we then fed that back into our control group and then back into the TEF. What else did I cover on that one? Yeah, so yeah, that worked really well. But it wasn't without challenges. You know, we're quite, as a communications group, we're quite low on the pecking order. And, you know, life safety is obviously number one. You're making sure people, you know, get people out of floodlands. Power was number two. Transport, heat and, you know, gas, etc. And then we're at the bottom. So from a, you know, we need resources point of view, we were almost shit out of luck in a lot of cases. You know, we wanted to get things on Hercules, get, you know, cell sites on wheels. We wanted to get staff and trucks on back of Hercs and all that sort of stuff, and we struggled. We were literally at the bottom of the pecking order. So very quickly, as an emergency forum, we realised that we were pretty much on our own. So, damage report. And this is what I felt like every morning when I woke up and basically said, you know, guys, what is going on? Where are we at? So what I've done is that since most things have been worked on as groups, I haven't done this in chronological order, but I'll just go through each region at a time. So Taupo. So in Taupo, we use Chorus. We use Chorus from the 2 degrees point of view, but we've also then got the old Vocus FX fibre, 2 degrees. That was still intact and operational. So from a Taupo point of view, our fix is pretty quick and pretty simple. We literally got a tech to the exchange, ran a jumper between 2 racks, don't tell Chorus, and got that live pretty quickly. So yeah, from a Taupo point of view, we were pretty happy. And the Chorus, you know, outages, I think were related to it. One was a fibre cut and one was a DWDM outage. I think it just happened at the same time. It was just pretty unlucky, but yeah, either way, we were offline on Taupo. We managed to get that on pretty quickly. Napier. Now, Napier was not pretty. So we have 6 fibre cables going into the Napier exchange. 5 were cut. And how much diversity and how much resilience do you need to have to survive this type of thing? You know, most people from a BAU point of view, you build a north and south pass, you look at your paths into the building, out of the building, what streets they're going to take, etc. But we had 6 and 5 of them got cut. So our Napier Taupo fibre, which went down the State Highway 5, that was cut multiple times. Our Hastings fibre, I've got some more details on this stuff in the later slides, but it goes across the rail bridge. The rail bridge was washed out. We had an IOU that went from Napier to Wairau via the East Cape. That was also gone. And then Chorus, which then used the same paths as a lot of our fibres, also taken out as well. So the only fibre we had operational was a 10 gig service that was never supposed to be a a transport network, which was went from our our Hastings bunker to the Hastings Exchange through an MX-80 and then into the Napier itself. So that pipe at 10 gig, when we used to have several hundred gig, was running extremely, extremely hot. And then 2 degrees was completely offline. So at the moment, we only had the Vocus network going, and then all our management was down. So we were pretty much blind. And in saying that, the power was totally out inside Napier because of the Transpower grid emergency, and I'll cover probably a bit of that later on. But more important to note, we had determined that we were missing 5 staff members, and 3 of them were in evacuation areas, and I'll touch more on that a bit later on as well. So here's a picture of our fibre. So as you can tell, on the State Highway 5, this is the Napier Taupo. It was pretty much toast. You can see on the left-hand side, most of our stuff was in rail corridor. The rail corridor really just didn't exist anymore. You can kind of see with a bit of help with the laser, that's our fibre sitting there. That was the road that it went on. That road no longer exists. And then went across quite a few bridges, and it was just covered in slash. The thing was just totally toast. This is our fibre went south. So that was the rail bridge, which was the rail bridge. And this one here was the remainder of the main road bridge that was there. It was just literally covered in slash. And yeah, our cable was no longer there. Our cable that we're hanging off, the 10 gig chorus fibre, was running along this bridge. So that was pretty much, so it was great concern, right? So, what happens when someone comes along here with the grader and tries to clear that road? Is that going to then take out that chorus fibre and then take us offline? So there was, pretty great concerns that we're then also going to be completely offline in Napier. Gisborne, not much better. So Gisborne has 2 fibre paths, one that goes from Whakatane around the East Cape and then down into Napier, down into Gisborne, and then there's one that went from Gisborne to Wairara and then Wairara to Napier. So the ones, they were both cut. They're a chorus fibre. We have an IRU on those fibres. They were completely offline, and from a power point of view, we actually had no visibility of what the power was doing down there, and we also had 5 2-degree staff missing. This is some photos courtesy of Chorus. This is taken around the East Cape. So as you can kind of see, the bridges were down. The fibre takes bridges, just happened to do that, and then a lot of flooding and slips all the way down there. So yeah, again, that fibre path was toast. I haven't got any photos of the Wairara one, but it was pretty much the same. Right, so let's crack into it. So let's just talk about what we did to fix it. So Taupo, pretty straightforward, bridge the 2 networks, simplest fix of all. Won't even go into much more detail on that one. In Napier, we did much the same. We had to bridge the Vocus and the 2 degrees network. That made our 10 gig circuit run quite a lot hotter than it already was. But with a bit of simple quas, we were able to get the mobile network up and running. And then, power issues, get generators deployed on there. And start getting those towers back up. So we had contractors down there doing that. But with generators, they generally only last about 8 hours before they need refueling. So we literally had to have teams of 3s, to cover the 24/7 and rotating around to keep all the generators full. And that was an exhausting job for the guys. And then we also had our Hastings optical bunker that needed refueling every 48 hours. But of course, with that bridge being the way it is, we actually couldn't get the guys in there to refuel it. So we actually ended up using the Unison guys. And the Unison guys knew about it, but of course there's no cell phone coverage. So those guys literally had to go and wave their hands in front of the cameras every 48 hours and let the guys let them in. And then there was a whole heap of access issues as well. The bridge that was carrying our fibre, had integrity issues. It still has integrity issues. You could only drive on one side of the road inside that, over that bridge. So there was great concern that that bridge was going to disappear at some point. And then there were fuel shortages as well. So while we couldn't get fuel, no one else in Napier could get fuel. There were literally fisticuffs on the forecourts of some of these service stations, and listening on the Lifelines meetings, there were literally people fighting over jerry cans of gas, and the fuel people basically begging for the army to be brought into the fuel stations. That also then created another issue where the Napier Exchange, which all of us relied on, that was also extremely low on fuel, and there was quite a bit of panic about trying to get those places refueled. And then just to make matters worse, we keep getting our generators stolen. We lost 3 over those 2 weeks, and generators being generators, that they're very hard to replace quickly. And then, yeah, that site's down. Well, we then have to try and relocate another generator. So that then has an impact on the people of Napier. So let's have a quick talk about the fibres. So this is the, I'll probably mark up the pronunciations, the Atatoto Bridge. But we had to run a 1.4 kilometre overlay across the dodgy, across that dodgy bridge. It's called the dodgy fibre overlay for a reason. And that bridge was open and closed through the week, which gave us massive headaches from an access point of view, and the police were very cautious about our presence on the bridge as well. When we first turned up to actually run the overlay, Civil Defence had put in a whole bunch of cautions. They had told the police, do not let anyone in there without special paperwork, but also in their great wisdom didn't tell anyone how to get that paperwork. So we were struggling quite a bit. We actually lucked out because we had our fibre guys there standing on the side of the road, blocking the road, because it's only one way in and one way out at the time, on the phone to me going, how do we get past these guys? And then a big fuel truck turned up, and then the cops looked at the fuel truck and went, shit, we need to get there through. You can go, just don't tell anyone. So we managed to get our fibre guys onto the bridge. And they were then able to run that 1.4 kilometre overlay, 2 splices on the end of that, and I think I was talking to, believe it was Wednesday night, possibly Thursday night, we then had some more bandwidth into Napier, which made things much easier for us. Napier Taupo Highway. So this one was a mess. So it was cut 13 times up and down that path. It required 25 kilometres of overlay over those 13 different paths, and then it required 26 joint enclosures to be put into the ground. And every time you did an overlay, you can't bury it, you then have to string it across trees or get it off the road as much as you can. So it was a pain in the arse. And the road was totally munted, essential services only. And it was hot, very, very hot. The guys literally having to wear their full overalls, and they're having to wear masks because of all the silt and all the health and safety risks that come with that. And then very later on, it started to rain, and those guys were cold. Very, very cold. They were working 12 to 15 hour days, and there were 30 of them working on the road at the time. Basically, most of them rolling the overlays or jointing, and we had major health and safety concerns for those guys because there were reports of people getting chemical burns in the floodwaters and just working those long hours. Health and safety being our health and safety, had all these wonderful good ideas. Let's go, give them drivers, let's call them an Uber so they don't have to drive home. But had to remind them that these guys, having to drive in their 4-wheel drives out to these places on essential service road only access. So there's no way that we could ever get them an Uber. And then we also then had to feed them as well. Try to get, the last thing you want to do is after 12 hours or 15 hours come home to your caravan or wherever you're staying, because there were massive accommodation issues down there at the time. And so trying to get them, feed and water and food was a major issue. And even now, even with the overlay on place, we're still getting our fibre cut probably at least once a week. Just from roadworks and I think the last one, I think it hit the spark one, not ours, but a farmer was trying to reinstate his fences and dug through the fibre. So there's still a lot of risk inside that fibre. Here's a picture of some of the stuff they had to deal with. You can see the guy literally stringing fibre along the fence to try and bypass some of the slips. This is my favourite photo of all of them. It's the girl power in action. The girl sitting there splicing away and all the lads watching her. We're actually going to try and find out who she is and actually bring her to our Women in Tech event to actually talk about her experiences on the road. As you can see, it's a pretty hostile environment that these guys and girls were having to work on. And here's a picture that Tim Harmon took for me. This is a picture, I don't know if it's our splice enclosure, but it kind of highlights the picture quite well. There's 26, on our network, there's 26 of these up and down that road, and then the fibre then shoots up the road to try and keep it away from everyone. So a lot of work went in from these guys. Let's talk a bit about Gisborne. So Gisborne had no road in and out of there, it had no fibre connectivity. The only way in and out was by helicopter. So we managed to find guys from Broad Spectrum, Broadtech actually, I think they were called, and there were 2 ex-SAS guys, and we literally said, hey guys, we actually don't know we want to fly into Gisborne, we need to take some generators, we need to take some Starlink kit, we need to take all this stuff. We're going to fly you in, we have no idea where you're going to stay, we have no idea how you're going to get food and water, are you up for it? And they basically went, yep, we're keen. Don't tell the health and safety people that, because they wouldn't tell them that, but yeah, they literally were flying into a disaster zone, and yeah, as you know, there was no comms, there was no FPOS, there was a cash environment, it was pretty nasty, and it wasn't like we could call up the local accommodation people and book a hotel. It just wasn't going to happen. But it went well for them. And here's a picture of Yako in his first night. He managed to get the Starlink up for himself and a small pico cell off the side of the hotel, and that was serving a bit of Gisborne at the time. Yeah, so that was a pretty cool experience to be part of. But the comms down there was madness. Talking to Yako, Vodafone had done a very similar thing. They put a pico cell outside the police station and also at the airport. And from what he's saying, there was about 400 people gathered around the police station trying to get a scrap of Vodafone signal at the time. So that just shows you how dire it was down there. So we were very lucky. East Cape, around the East Cape, we managed to get online pretty quickly, and that was thanks to the work of Cordia. We used Cordia for backhaul on the East Cape, and they did a lot of work to get generators online, and we were able to get their DMR stuff back up online and get our East Cape. We were able to then, actually just going back to that quickly, so we actually called them the SEAL team. So if you have someone at 2 degrees talk about the SEAL team, we called them SEAL Team 2 because 2 is better than 1. We can't call them SEAL Team 1 for obvious reasons. But yeah, so anything we talk about here is effectively what we call the SEAL team. So the SEAL team went into the Gisborne Exchange. They're able to patch our central exchange, which is on top of the post office building, into the Cordia backhaul, and that allowed us to get the first macro coverage up inside Gisborne Central. So a big thanks to Cordia, and then with a bit of reconfiguration, we managed to drop our East Cape requirement down from 4G to 3G, and that allowed us to then reconfigure Gisborne Central to give us 85 meg of bandwidth. And 85 meg of bandwidth doesn't sound like a lot. It's not a lot when you're talking about a 4G network, but was enough to then get people connected and phone calls, etc., working into Gisborne, which was, we were the first telco to get a macro working, which gave us good coverage good coverage in Gisborne. We also then worked on a Starlink site, so we ended up getting the guys to go to a place called Riverdale, which is just down the road from Gisborne Central, and we're then able to get Starlink up on a BBU and then get Starlink up. And then meanwhile, much later on in the piece, I'll touch on this a bit later, we actually won what I call the fibre lottery. We, around the East Cape, we actually have a fibre that dashes up the cliff, it goes to one of the Cordia pops and then comes back down again. And those fibres were the first to get spliced, and that allowed us to bring Gisborne back online as a whole. Admitting a bit later on, but we were the first one to get fibre up in Gisborne, and they were just extremely lucky that join bypassed the damage that was on that cable. So we effectively had a day ahead of the others just because we won the fibre lottery. Talking about dodgy fibre overlays, this is the Chorus one that went across the East Cape. Very hard to see, but it was literally strung with a helicopter. You can see it just sitting above the trees here, right? So this is kind of the stuff that everyone had to think outside the box with to try and get Gisborne back online. The pressure that Chorus were getting to get Gisborne back online was immense. Obviously all the telcos were saying, hurry up, hurry up, hurry up, but also the government was also saying, you need to hurry up. Anarchy's going to start in Gisborne unless we start getting FPOS and all that stuff online. Here's a picture of our Starlinks install. This is our Riverdale one. We had all sorts of fun with Starlink. So we got it, it worked in the lab, didn't work in production, as you probably all heard that saying. It was very true in this particular case. And it was just silly things. So we tested it in the lab, the Huawei stuff, this is all Huawei kit. We managed to get it working in the lab, get down there. The requirement from the guys is to literally reconfigure the BBU. We had to lower NTUs, we had to change IP addresses. We had to effectively use our second Starlink to allow the guys to then console into the BBU to change the IP addresses and reconfigure it and then plug the Starlink directly in. And that worked fine the first time. What happened next is we took the second Starlink to the second site. What we've forgotten about is Starlink is geo-locked. So when the second one moved, it went, oh, you've moved, sweet, and then locked both our Starlinks out. So we then had that back to square one with no coverage on that site. Once we managed to get that sorted with Starlink, we then had to go reconfigure the BBU because the IP address had changed. So that was then again a pain in the ass. But what we did there is we actually ended up putting a 40 net in front of it, and that allowed us to then build the tunnels back to our head office. And then if the IP addresses did change, the 40 gates were far more prepared to sort that out. We haven't tixered that yet. We're going to tixer that soon, after a little reminder soon. I know, I was going to claim that, yeah. And then once we managed to get that fibre back up, we then actually started to move on Wairoa. So if Chris is still here, we've got toys too. And so the guys were then able to get up to Wairoa and then get our Starlink up at line. This actual Starlink is actually still up at Wairoa, not because we haven't got fibre connectivity there, we just kind of felt like it's a good test to keep that running to see how viable the Starlink is in the future. So touching on good things that happened, there are lots of good things that happened. This is Cliff from Vodafone and Justin up there. They managed to refuel one of our generators just off the goodness of their heart and then send us an email saying, we really hope we didn't put petrol in your diesel generator. Turns out it was a petrol one, so we're all good. But so yeah, thanks Cliff for the help there. And we also then had other people also refueling our generators as well. We had a farmer who every day would make it part of his routine to go down and refuel one of our generators on our south side. I'm assuming he must have had kids on his fixed wireless access because he wanted to keep really desperate to keep it going. And talking about people, right, so we had 5 people missing, like 10 people missing. We eventually did find them, and that was thanks to our service partners because we sent out the call to Ventia and Avtela and a few others to, can you help us out? We had logged police reports for these 10 people, but the police were just overwhelmed with the amount of people that were lost. So we actually then ended up getting those guys to go and door knock on these guys to figure out where they were, what they needed. This is a picture of our welfare team, and they actually then flew down to Napier, and the request from the Napier people was, literally send batteries, send bottled water, send whatever you can. So we actually then flew 2 people down with all these people, and here's our team down there giving each other a bit of a hug. And then on the left-hand side, here's every single PowerPoint you could find in the Curry Lounge charging batteries. And they were very grateful. The people in Gisborne also got found as well. So we ended up, not having any losses, thankfully. But 3 people lost their homes in this as well. So yeah, thoughts to them. But in the end, it was all pretty much worthwhile. All of us worked pretty long hours. The incident team, basically we worked for 2 weeks non-stop. We were working 7 a.m. until 10 o'clock at night, and then get up at 7 a.m. in the next morning and crack into it. So my wife and kids didn't see me much, and when they did see me, it was pretty much on the phone. But this sort of stuff, this was a Facebook post, this pretty much made it worthwhile, right? You've got people out there saying, thanks to 2 degrees, we're able to make contact with our loved ones down in Gisborne and Napier. So, reading that sort of stuff made you pretty humble and pretty thankful for what we had and what we could do for these people. So, yeah, that's me. Any questions?
Is this the 3-day SLA starts?
I'm not looking forward to this one.
Did you find your generators?
No,
they end up?
They're still missing. Yeah. We did actually end up putting ear tags on them, but they found them and threw them off. So we never tracked those again. Spark lost generators as well. They had GPS on them. They know exactly where they are, but with the police being overwhelmed, they never got them back either.
Simon.
Yeah.
Not a question, but a thank you from people in our region, and to you and your TEF colleagues. I was lucky enough to sit on some of those calls, and it was a pretty good team, working hard to get comms back to people of Hawke's Bay and region and Gisborne, It's amazing how isolating you feel when you can't communicate with anyone. So it was, I really appreciate your effort. And for everyone else, Hawke's Bay is very much open. The wineries, most of the wineries are still open. So come on down, I'd love to see you.
Awesome. And I guess one last thing I haven't mentioned, and it's probably, we talked about the minister at the start. Melissa Lee, who was a Green MP, she actually put a motion out to the floor to thank the people of TCF, which is mainly you guys, and a Whisper to say thank you for the efforts, and that went to the floor nomination. So yeah, I guess we did get a lot of thanks from the government for the response as well, not just from a 2 Degrees point of view, but from an industry point of view.
Not really a question, but really from the team, we wish to, wish you a happy birthday.
Oh, thanks, man. Cool. Is that it? No, still more.
Yeah, I'm just wondering if you heard about any oddball customers coming in with really strange complaints, because I know that we had one where he kept calling in because the gen sets were keeping him up at night, apparently. He wanted us to turn them off overnight for him.
Yeah, no, we didn't, thankfully, but that could explain why some of them were stolen.
Thank you, Simon. From going through this, how has this changed your BCP process?
Yeah,
and what are the major things you learned?
Yeah, that's a good question. So we learned a lot. A lot of it was around processes and data. We realised that we've got quite polarised data. So yeah, our RAN team know exactly what the RAN's about, but when we asked them transport questions, they basically looked at us blankly and said, talk to the transport team. So there's a lot of work going to go around consolidating our data, so we actually know what's, have a full end-to-end picture, because otherwise you've got to have 2 people involved rather than 1. A lot of it also comes down to real-time status views for our customers as well. A lot of it was manual processes, and trying to keep up with all the outages was too hard for the knock-at points, so the status pages wasn't up to date as much as what it could. So it's going to be a lot of work around visualization and automation around outages, etc. And probably the third one, again, it comes down to documentation. Turns out not all our sales sites have generator plugs on them, so there's going to be a bit of a retrofit, making sure that we do have that sort of, and documented of where they are as well. So there's a list. We came up with a list. That was probably the top 3 technical ones anyway.
Coming from, I'm sort of emergency services as a side hustle, volunteer.
Yeah.
In Auckland, word on the street was that LPG was not a problem on the East Coast. Petrol and diesel would run out, but LPG was still freely available.
Yep.
Do you know, are you able to confirm if that was true, and if LPG is actually the way forward for generators?
Yeah, from what I could tell, there was definitely no panic over LPG. They seem to have lots of stock. The biggest problem they had was getting it out to customers from a transport point of view with all the road closures and stuff. But yeah, on the calls, the LPG guys seemed pretty happy. There was a bit of concern at one stage because they've got a pipe going across that Atatua bridge. So there was a concern around delivery of, getting it around the places from a pipe point of view. But yeah, it was definitely easier to get than petrol at some points. One at the back.
Have you guys put any further thought into diversifying your transit options with other providers except the main ones to avoid what happened in the future?
Yeah, from a fibre point of view?
Or no, from a wireless DMR point of view, because there's obviously 37 plus WISPs in the New Zealand market now.
Correct,
and
yeah.
most of them are providing services to like the likes of RCG and Cordia. And,
absolutely, yeah. So those sort of things will go into the pot really to think about. 2 Degrees is also a fixed provider as well, right? So we trying to use our high capacity links and mobiles, obviously a small fraction of that. DMR doesn't support the fixed. It'll support mobile quite nicely in some cases, but it doesn't support fixed. So there'll definitely be thought about how we use DMR in the future to keep mobile up and running. But economies of scale and cost also come into consideration as well.
Anyone else? I think that's about it.
Sweet. Awesome. Thank you, guys.
So we have some lightning talks now. I think we've got 3. Yep. And I think we decided Joel first. Excellent.
Tēnā koutou katoa, ko Joel tēnei. Ko taranaki te maunga, ko Pātea te awa, ke Pauneki tōku whare. Kia ora, my name's Joel. I work for Red Hat. I'm going to play you some marketing bullshit for about 1.5 minutes because it's got music, and I thought that would be more interesting than showing you the demo of the thing I'm going to talk about. So if you could play the little video I've got, it's only 1 minute, but it's better than the code on screen. Jeez. Okay, enough whiz bang. Now to the dystopian hellscape we are living in. So I'm going to chuck my slides up. This is just a talk about large language models. Now, everyone I've talked to this week has something to say about GPT-3 and one of the implementations called ChatGPT-3. Copilot's another GPT-3 based derived product. And that's a particular model that's been trained by our friend Papa Elon and his lackeys over at OpenAI. Now, it's a useful tool, don't get me wrong, but I think one of the things I have as a ex-computer scientist and recovering computer scientist, I get, is that this is not new technology, this is old. I mean, I was teaching my Info 101 students back in 2006 on the basics of neural nets, and that's pretty much what's going on behind the scenes between these large language models. And what it is, and this is a networking conference, so I'll use a networking analogy, is nodes and edges. So basically you're weighting the edge between a node, and the node is the corpus that you're teaching it, right? And you're just doing this repeatedly over and over again and building up responses that it's deciding on its probability kind of perspective that it should push back to you. Now, we've gotten quite good at doing this for voice recognition, and there's a whole kind of subset of CompSci around voice recognition and speech synthesis, and so we've trained the models to get good at doing natural language using syntax and grammar rules, and then we've started to train them on these large corpuses. That's cool. If you understand that, then you'll stop using it for things like telling you, what was the thing in John? What was the, you had a terahertz, John yesterday put a little kind of Easter egg in his slide, and what was it? You asked it to tell you how many meters or millimeters a 100 terahertz wave was, and you took it at face value. That's the sort of question you don't ask ChatGPT without verifying it, unless you have, unless you have the expert knowledge to understand those expert questions need to be vetted. So there was a really good talk from Arista this morning, our good friends at Arista. They're a Red Hat partner, good work. And they're talking about AI for doing network ops, which is a really good use case, but you need to train the models properly. If you could go to the next slide, whoever's running my slide deck for me. Cool, we did this already. So we went, cool, what happens if we ask GPT-3 to make us playbooks? which is YAML, which is Ansible. And we asked it to do something quite simple, deploy me a rel instance to Amazon. And it dutifully went off and gave us an example of a playbook that would do that. And then we went, let's grade it. So this is a really cool blog article. We sort of go through and look at the mistakes it made, and with an expert view across the thing that it was doing. It was good kind of struts. I mean, I think for getting halfway there, if you really know nothing about YAML, it's a good place to start, to maybe go and ask it and give you some examples. Okay, cool. So we can't get general purpose kind of coding out of these things, and probably never will in a way that's reliable if we're just using a general purpose language model like GPT. But we can train it with a decent data set that we do vetting on to do specific things. So that's what the Project Wisdom demo is there. We still haven't productized it. It's in tech review. We actually just launched an open beta this morning. You can sign up if you've got a GitHub account and get access to the hosted version of it. We're not sure how we're going to productize it. It probably will get rolled into the Ansible linting tool, which is part of VS Code. It works pretty well at the moment, but it's got a way to go, and it will give you playbook results. So we're relying on our certified content that we already have and our customers that have contributed to the corpus of the engine behind it. And of course, IBM has been doing this for decades. So we have the backing of the Cognitive Behavioral Lab, which is nice because it gives us a bit of a head start. But things like the Arista talk that we had this morning, which was talking about AI ops for writing network code, this is exactly the sort of thing that we're trying to do and make it a low barrier thing as well. So this is the sort of thing that you might be able to give to your junior network technicians that have no automation experience, and you go, here, go tell the VS Code plugin with Project Wisdom sitting behind it. So this is kind of a neat thing, but I guess there is a whole dystopian hellscape behind this as well, right? And I think some of those ethical questions that I put my other hat in, which is, I'm a member of TOTO, which is a misinformation monitoring. We do, started off as Creative Commons New Zealand. We do a lot of copyright stuff. The Copilot tool, which is another GPT-3 based kind of product, was trained on a heap of open source code, which the contributors didn't actually say you could train your AI data model on. So one of the things behind Project Wisdom is that we're potentially looking at this as being something you could host yourself. So the core model for the actual playbook writing we'll be able to ship to you, maybe. I don't know, this is not actually a product yet, but they're potentially looking at it so that in secure environments, say someone who runs core infrastructure and is under TICSA regulation, for example, you could use this internally on your own hosted kind of OpenShift Kubernetes style cluster, deploy the data model, and then plug it into your Ansible platform. So this is the type of thing that we're looking at doing because there is a bunch of ethics and where did the content come from, how was the AI trained, what content was it trained on, and if you're a Department of Defence or a core infrastructure provider, those are questions that are pretty valid. But yeah, that's pretty much it. I'm giving a more in-depth talk about this next week in Wellington, and then repeating that again in a couple of weeks. So a bit of a plug for the events that we've got coming up. So when I move to the last slide, there's like a registration link at eventshub.redhat.com. And this has been repeated in May, but this is next week. If you're a Wellington base, come along. It's a bit more of an in-depth what's happening with Ansible in general. There's some other cool things about event-driven automation, so that's been able to plug into things like Grafana or Splunk or a file handle or a post data and actually react to those things, which is a brand new thing in Ansible that we've introduced upstream in the last 6 months. So it turns Ansible from being something that just does automation to something that you can drive using a messaging platform. So that's quite cool as well. So that's me. Any questions? No? Brilliant. Thank you for my marketing bullshit.
Right, Matt from, what are we saying, IA, NZAX? Both. Yeah, right. Should we, yeah, I'll give you this.
All right. Just following on from my presentation yesterday, I had a couple of questions from people about circulators, optical circulators. What are they? How do they work? Love the heckles. So I thought I'd give a little bit of a prezzo on just what they are, how they work, what we'd use them for, how we use and abuse them. So basically they look like a three-legged patch lead. Got a little tube in the middle which contains all the clever optical stuff. Light that goes in one leg is circulated to the next leg, hence the name. So yeah, light entering port 1 goes out port 2, and port 2 in goes out port 3. You connect port 1 to your SFP transmit, port 3 to your SFP receive, and port 2 becomes your line side, which goes to your dark fibre, cross connect, whatever it might be. It gives you duplex transmission over a single fibre core. Again, more photons for your dollars. They are not terribly simple internally. I actually did a little bit of research, or quite a bit of research actually, into how they work. This was as much as I was able to condense it down. So light going into port 1, which is blue on the diagram there, splits into orthogonal polarizations. You get a net 90-degree clockwise polarization shift going from port 1 to port 2. Going through the Faraday rotator gives you 45 degrees, and the phase plate gives you another 45. The rays are then recombined at the other end and sent out port 2. Going the other way, however, you get a net 0-degree polarization shift. So it comes in, split again into orthogonal polarizations. Your phase plate gives you a negative 45-degree shift, or anti-clockwise. And then the Faraday rotator does plus 45. There's your net 0. And then it's recombined and sent out port 3. And that different polarization shift in each direction is just for isolation of the rays going in each direction. So what have we learned from using them? Distance that you can use them over is limited. 10K is a good rule of thumb. We have tried doing it over long distances, most recently with 40 gig R4s over about a 30K link. It just wouldn't work, wouldn't come up. So your mileage may vary quite literally. And take care when patching it in. So if you plug them in the wrong way around, ports 1 and 3 into the SFP, you'll get a literal loopback. Recommend that you do bench patching first, so set it up on the bench before you actually plug the SFP into your gear. Fibre breaks will give you light reflections, which means that your interface might not even go down. So don't rely on just interface up, down if you've got circulators on. And it can also cause a bit of weirdness if your gear doesn't like seeing itself in a mirror. Let's face it, who does like that? APC versus UPC ends. So I'm talking about the blue versus green connectors that you see on your fibre patch leads. The APC or green leads for the circulators are the best ones to have wherever you can. Reason being that they are angled, so it stops the light reflecting off a disconnected patch end, which will then give you that light coming back in on your receive leg. Whereas the UPC ends do actually act like a mirror because they're a flat surface, so they give you that reflection. And we've actually got new products on the market now. So when we first did this sort of stuff, 100 gig BiDi wasn't a thing, and that's why we did a lot of it. Flex Optics, our SFP provider, they've since released a 10K 100 gig BiDi QSFP. We use these in the IX Australia network in Brisbane. I actually installed them not that long ago, and they do work exceptionally well. So we're able to use those now instead of circulators, which are a bit more janky. Thanks very much for that, guys. Anybody got any questions about that?
I knew John was going to have a question.
Look, I'm just going to say that circulators come in all sorts of qualities. The first time I used a CWDM with packaged circulator was in 2012. Those are still deployed. They came from Shenzhen Gigalight. Very nice product. So you get an 8-channel CWDM mux and a circulator in one. Of course, it's all APC, green connectors, and you just go for your life. The link budgets are deterministic. It's not something that you have to guess at. These days, Gigalight is not responding to my emails to try and buy more. The last time I bought more was 2018. I bought a bunch in 2018. Since then, I've found that Starry Optics will sell me something that looks just like this. And one of the large carriers in this room has used those in their network because Starry Optics marketing materials has a picture of one of those at Merrill Drive. So they're not uncommon.
There you go, fantastic.
And others?
Why would you use a circulator nowadays when you can use a DWM over a single?
Look, if you've got, like your LR optics obviously are relatively cheap. I know the DWDM optics are also quite cheap as well, but it's all the ancillary costs that go with that, whereas a circulator is quite a cheap option. So that's one of the main reasons I think why you'd use that these days. But again, as I said, now we've got the bi-die optics coming out in 100 gig flavour as well. So they're a pretty cost-effective option too, and that's why we opt to go with those more often nowadays than anything. But it's good to have as an option, yeah.
That is all.
Cool, thanks guys.
So our third lightning talk has gone to the airport. So that is all. So we finish now for, we've got some afternoon tea, but I think, yes, and that's it. So thank you all for coming. Do I need to say anything else?
We were going to try and announce what was happening next year, but then I rashly promised somebody on the Slack list that we would consult over March. So we're going to consult over March. We're going to try and go to the South Island. It is getting harder to find venues that take this number of people and have desks who already have laptops in front of them. So we'll see what we can do. But yeah, maybe the South Island, maybe March, if everybody's still happy. So the survey will be out shortly. Yep. Okay, thank you very much. We're all done.